chocolate, caramel, and peanut butter collide in a masterpiece of modern candy engineering. From molten chocolate streams to precision peanut butter layering and caramel-filled molds, every step is timed to perfection inside colossal confectionery factories. Today, we uncover the hidden machinery and sweet science behind Reese's peanut butter cups, Oreo cookies, and Snickers bars, and reveal how these legendary treats are made on a massive scale. The process starts long before chocolate or peanut butter ever meet. At the peanut processing facility, tons of raw peanuts arrive in burlap sacks and bulk containers, fresh from southern farms where the plants were pulled from the soil, their pods dried in the sun. The nuts are cleaned to remove stems, dirt, and any lingering bits of shell. Then they pass through roasters, enormous rotating cylinders that blast them with hot air. Inside, the peanuts swirl constantly, heating evenly, transforming from pale beige to golden brown. The smell that fills the air is unmistakable, toasty, buttery, comforting. A scent that has come to define American candy culture. Once roasted, the peanuts are quickly cooled with air jets to halt the process and lock in their flavor. They are then blanched, which means their skins are rubbed off mechanically while their tiny hearts, the little germ tips at the end of each nut, are removed to prevent bitterness. What's left are pure, smooth peanuts, ready for grinding. Grinding peanut butter for Reese's isn't like making the jar you spread on toast. The factories use custom grinders that reduce the nuts to a coarse, almost sandy paste. The texture is deliberate, not too smooth, not too oily, because this peanut butter needs to hold its shape inside a chocolate shell. It must be thick enough to bite cleanly, yet soft enough to melt on the tongue. A precise amount of sugar, salt, and hydrogenated oil is mixed in to balance sweetness and texture, creating the signature Reese's filling. Salty, sweet, crumbly, and rich. The temperature of this mix matters immensely. If it's too warm, it becomes oily and difficult to form. Too cool, and it won't spread properly into molds. Meanwhile, in another section of the factory, chocolate is being prepared. Giant mixing tanks melt and temper the chocolate coating that will form the outer shell of the peanut butter cup. The chocolate itself is a blend. Milk chocolate made from cocoa liquor, sugar, milk solids, and cocoa butter. And it must be tempered perfectly to ensure the final candy has a glossy finish and that distinctive snap when bitten. Tempering involves heating and cooling the chocolate in precise cycles so that the cocoa butter crystals align in their most stable form. At full scale, this is done with computer-controlled tempering machines that maintain the chocolate within a tight temperature range, usually between 30 and 32 degrees Celsius. With both peanut butter filling and chocolate ready, the assembly line begins its hypnotic rhythm. Thousands of paper cups, those iconic brown wrappers, are unrolled from stacks and dropped one by one into shallow molds traveling along a conveyor belt. Liquid chocolate is then dispensed into each cup through a multi-nozzle depositor, creating a thin base layer. The machine moves with astonishing speed and precision, filling hundreds of cups per minute, each portion measured to the gram. Immediately after, a brief vibration shakes the line to smooth the chocolate and remove air bubbles, ensuring a uniform bottom layer. Next comes the peanut butter filling. Still warm and pliable, the peanut butter mixture is extruded in neat, circular dollops directly onto the chocolate base. It's not liquid, but not solid either, more like dough. And it must land perfectly centered so that the chocolate can later seal around it. If the peanut butter shifts or spreads unevenly, the final cup will lose its symmetry, something the factory's sensors and cameras are quick to detect. The line hums along as each layer is laid down in sequence, the smell of roasted nuts mingling with melted chocolate in an aroma that seems almost engineered to trigger nostalgia. Once the filling is in place, another layer of liquid chocolate is poured on top, completely covering the peanut butter and meeting the edges of the cup liner. The top layer must be the perfect thickness, too thin, and the filling might peek through. Too thick and the chocolate will overpower the flavor balance. Another round of gentle vibration ensures a smooth finish before the cups pass into the cooling tunnel. A long, chilled chamber where the temperature gradually drops. As the cups travel through this tunnel, which can stretch over 20 meters, the chocolate solidifies into its final form. The cooling process has to be slow and even. If it's rushed, the chocolate could bloom, forming a whitish coating of cocoa butter crystals that looks harmless but gives the candy an uneven appearance. Inside the tunnel, the air is cool, dry, and filtered to perfection, and the cups emerge shiny, firm, and ready for wrapping. From there, the candies head into wrapping machines, intricate systems that feed foil and paper labels at high speed. Each cup is picked up, cradled between rollers, and swiftly wrapped in its familiar orange and yellow packaging. The process happens so fast that human eyes can barely follow it, and yet each wrap is tight, centered, and perfectly printed. The final wrapped candies tumble out of the machines in cheerful heaps, moving onward toward boxing and distribution. Before they ever leave the factory, though, random samples are pulled from every batch for quality testing. Workers in white coats cut the cups open, inspecting the cross-section for proper layering and balance. They check that the chocolate coating thickness falls within tolerance, that the peanut butter center hasn't dried or separated, and that the taste is exactly as it should be: salty, sweet, and slightly gritty. Even the sound of the bite is evaluated, that gentle, satisfying resistance of chocolate giving way to soft peanut butter. Behind all this precision lies a history that began much smaller. Reese's peanut butter cups were invented in the 1920s by H.B. Reese, a former dairy farmer and Hershey employee who started experimenting with candies in his basement in Hershey, Pennsylvania. At the time, pairing peanut butter and chocolate wasn't the cultural phenomenon it is today. Reese saw the combination's potential early on. The contrast of salty and sweet, creamy and solid. And when the candy gained popularity, he devoted his entire production to it. Over the decades, the process scaled up dramatically, but the formula stayed nearly the same. What once required hand-filling paper cups with a spoon is now done by multi-million-dollar machinery capable of producing millions of cups a day, yet the goal remains identical: a perfectly balanced bite of chocolate and peanut butter. Inside the modern Reese's factories, that legacy hums quietly in the background. Every detail of the process, from the way peanuts are ground to how the chocolate flows into its molds, is the product of decades of refinement. Engineers spend years fine-tuning depositors so that peanut butter centers always stay centered. Sensors measure chocolate viscosity in real time to ensure the coating flows just right. Even the paper wrappers are engineered to peel cleanly without sticking, their ridged edges pressed into the chocolate to create that unmistakable ripple pattern that makes a Reese's instantly recognizable. The scale of production is staggering. In large facilities, conveyor lines stretch for hundreds of meters, running continuously for most of the day. Each minute, tens of thousands of cups are molded, cooled, wrapped, and boxed. The air temperature, humidity, and even airflow patterns are carefully regulated because chocolate is sensitive to the slightest variation. In the storage and shipping areas, finished candies are kept at controlled temperatures to prevent melting or bloom during transport. Pallets of Reese's cups move out daily by truck and rail, bound for every corner of the country and beyond, ensuring that a candy created nearly a century ago still reaches millions of hands in the same perfect form. Despite the industrial scale, there's something undeniably human about the candy itself. It feels handcrafted in spirit, a blend so simple that it borders on poetic. Each cup is a meeting point of two distinct worlds: the earthy, roasted hardiness of peanuts and the smooth, creamy indulgence of milk chocolate. The textures play off each other, the chocolate breaking cleanly, the peanut butter crumbling and melting. And it's this contrast that makes it so addictive. Factories can reproduce it endlessly, but the experience of eating one remains personal and immediate, like a small private reward. And that perhaps is the quiet brilliance behind the Reese's Peanut Butter Cup. It's both mass-produced and intimate, engineered for perfection yet grounded in comfort. The factories that make it run like clockwork, stainless steel conveyors, digital controls, robotic arms. But at their core, they exist to recreate a sensation that began in a basement nearly a century ago. The sheer delight of chocolate meeting peanut butter in perfect harmony. The story of an Oreo begins, as so many great foods do, with the ingredients flour, sugar, cocoa powder, and shortening all arriving in bulk, stored in massive stainless steel silos and containers. The flour is refined to be extremely consistent, with a specific protein content that affects how the dough will bake and how much it will rise. Oreo dough is not fluffy or light like bread dough. It's dense, dark, and barely rises at all. More of a sculpted material than something that expands. The cocoa used isn't just any cocoa. It's processed to achieve Oreo's signature, deep black color, and its slightly bitter, roasted flavor that balances the sweetness of the filling. This type of cocoa is known as Dutched cocoa, treated with alkali to mellow its acidity and intensify its hue. Even the sugar is chosen for its granule size, fine enough to blend smoothly, but not so fine that it clumps or melts too quickly under heat. Inside the mixing room, the ingredients are weighed with mathematical precision, poured into massive horizontal mixers that churn hundreds of kilograms of dough at a time. The sound is deep and steady, a rhythmic mechanical kneading as rotating paddles fold and crush the ingredients together. The air smells intensely of cocoa and vanilla. Water is added gradually, just enough to bind everything into a dense, pliable dough. Unlike many other cookies, Oreo dough has almost no leavening, no yeast, little baking soda, because the cookies must stay flat and crisp. Every grain of flour and sugar must blend uniformly, because any variation could affect how the cookies bake or how they fit together later on. After mixing, the dough is left to rest briefly, allowing moisture to distribute evenly, creating a consistency like soft clay. Flexible enough to shape, but firm enough to hold detail. That detail is important because each Oreo cookie carries one of the most famous surface designs in food history. The intricate pattern, the radial lines, the dots, the geometric petals, the word Oreo, raised proudly in the center, isn't just decoration. It's an engineering feature. The embossing helps the dough bake evenly by increasing surface area and ensuring consistent heat transfer. To achieve that, the dough must pass through a series of rolling and cutting machines that operate like synchronized clockwork. Sheets of dark dough move along a belt, passing under heavy rollers that flatten them to exact thickness, often just a few millimeters, before reaching the die cutters. These cutters press the pattern into the dough and punch out perfectly round cookies at high speed, hundreds every second. The excess dough is automatically lifted, rolled back into the mixer, and used again. Nothing is wasted. As the freshly cut cookies roll towards the ovens, they look soft and matte, their patterns crisp but still raw. The baking stage transforms them entirely. Oreo ovens are vast tunnels, long enough that a person could walk through them, divided into multiple temperature zones. The cookies enter on steel mesh belts and travel slowly through, spending several minutes surrounded by hot, dry air. The smell here is extraordinary. Cocoa deepening into its roasted form, sugar caramelizing just slightly, oil releasing its aroma. The cookies lose moisture rapidly, firming into their familiar, crisp texture. By the time they emerge, they've turned from soft dough to perfect wafers, dark, fragrant, and fragile. They cool as they travel along the conveyors, air flowing gently around them so they don't warp or crack. The cooling process is crucial. If the cookies were filled while still warm, the creme would melt, ruining the structure. Once they reach ambient temperature, they're ready for one of the most recognizable steps in all of food manufacturing, the sandwiching of the creme. The creme filling, store, and yes, creme is the official spelling because it's not traditional dairy cream, is its own carefully engineered mixture of sugar, oil, and flavoring. The goal is to create a filling that is both firm and soft, able to stay solid at room temperature, but melt smoothly when eaten. The base is made in large temperature-controlled mixers that whip the ingredients together until the texture is velvety and thick. The flavor is simple, sweet, with a faint vanilla note, designed to contrast the bitterness of the wafers without overpowering them. The temperature must be perfect. Too warm and it's too runny to spread. Too cold and it won't bond properly to the cookies. On the production line, everything moves in perfect synchronization. One conveyor carries the bottom wafers, patterned side down, while another carries the top wafers, patterned side up. Between them, a high-speed depositor extrudes precise dollops of cream, identical every time, onto each base cookie. The depositors use spinning nozzles that twist slightly as they release the creme, creating that familiar swirl pattern you see when you twist an Oreo apart. Immediately after the dollop lands, another cookie drops from above, pressing gently into place to form the sandwich. It happens so fast that in the time it takes to blink, 3 or 4 Oreos have already been completed. Once assembled, the cookies pass through cooling tunnels again to stabilize the cream and allow it to set. Inside these tunnels, chilled air keeps the temperature consistent while conveyor belts move continuously, carrying thousands of sandwiches at once. The noise here is subdued, a low mechanical hum punctuated by the faint clatter of cookies sliding along stainless steel. When they emerge, the Oreos are complete, uniform, firm, and fragrant. But before they're ready for packaging, they must pass quality checks. Random samples are pulled constantly and examined for weight, size, and appearance. Technicians measure the creme thickness with calipers, ensuring it matches the standard down to tenths of a millimeter. They check that the embossing is sharp and centered, that no cookies are cracked or uneven. Some are even broken open to inspect the bond between wafer and creme. If it separates too easily or too stubbornly, it signals an imbalance in texture or temperature earlier in the process. Taste testers sample from every batch, judging aroma, crunch, and sweetness balance. An Oreo that's slightly too crisp or too soft is rejected because even small deviations can alter the iconic twist, lick, dunk experience consumers expect. When the batch passes inspection, the cookies move towards packaging lines, which are as swift and rhythmic as everything else in the plant. Oreos travel single file into wrapping machines that form the familiar blue packages, sealing in freshness with nitrogen-flushed air to prevent staleness. Each pack is sealed with a combination of heat and pressure, cut precisely and labeled. The packages drop into cartons, cartons stack into cases, and cases are palletized by robotic arms that move with fluid precision, building towering stacks ready for distribution. From here, the cookies travel to warehouses and stores around the world, identical in taste and texture from one continent to another. It's remarkable that such a small, simple object, just 2 wafers and some creme, requires this much control and coordination. Every step is about balance, the ratio of sugar to cocoa, the moisture in the dough, the exact cooling time between baking and filling. The cookie's geometry is even designed for sensory effect. The thin wafers break easily enough to create a clean crunch, yet are dense enough to hold the filling without crumbling. The cream's composition ensures that when the cookie is twisted, one side usually retains most of the filling, a phenomenon studied by engineers who've even coined the term Oreology to describe the physics of how it splits. And through all this precision, the Oreo remains oddly personal. Its uniformity is what makes it universal. I'd say Whether dunked in milk, crumbled into ice cream, or eaten layer by layer, it always tastes the same. That constancy is what makes it comforting. Behind the bright blue packaging lies a vast orchestra of mixers, ovens, conveyors, and coolers, all tuned to recreate the same sensory moment millions of times a day. The soft snap of chocolate wafers, the sweetness of creme, the nostalgia of something known and unchanged. When the production line finally slows for cleaning or maintenance, the air still smells of cocoa and sugar. Workers in white coats sweep the last crumbs from the conveyors, and the factory quiets down, but the scent lingers. Warm, rich, unmistakable. It's the aroma of a century-long legacy, a combination of science and familiarity that has outlasted trends and imitations. The process starts with the nougat, the unsung foundation of every Snickers bar. In massive stainless steel mixing tanks, sugar, corn syrup, and water are heated until they form a bubbling syrup. Once the mixture reaches the right temperature, usually just below the point where it would begin to caramelize, it's transferred into a high-speed aerator. Here, the syrup is whipped together with beaten egg whites or a similar foaming agent, introducing countless tiny air bubbles that give nougat its light, slightly spongy texture. The mixture turns pale and fluffy, almost marshmallow-like, and at this stage, flavorings like vanilla or cocoa are added, along with a measured amount of peanut butter or milk powder to enrich the taste. The nougat is then spread onto a moving steel conveyor belt, still warm and pliable, forming a continuous sheet several centimeters thick. The surface is smoothed by rollers, and the air in the room smells faintly of warm sugar and roasted nuts. The nougat must cool for just the right amount of time. Too soft, and it will deform under later layers. Too cool, and it won't bond properly with the caramel. In candy production, texture control is everything. Meanwhile, a second part of the factory is busy with what might be considered the soul of Snickers, the caramel peanut layer. In large copper kettles, sugar is melted with milk and butter until it turns a deep amber color. Workers monitor the process closely because caramel is notoriously sensitive. A few degrees too hot and it burns. Too cool and it stays grainy. The caramel used in Snickers isn't the brittle kind that shatters, but a soft, stretchy variety made by carefully balancing milk proteins and sugars. When finished, it has a velvety sheen and a texture that pulls gently without sticking to the teeth. Before the caramel is poured, peanuts are prepared. Whole roasted peanuts, chosen for size and flavor consistency, are brought in from bulk silos and checked by electronic sorters to remove any imperfect ones. They're roasted in massive rotary drums until golden and aromatic, then cooled quickly to preserve their crunch. The peanuts are mixed into the hot caramel, tumbling in great churning vats until every nut is coated in a glossy layer of sweetness. The smell in this part of the plant is overwhelming, buttery, nutty, sugary, like a festival in the air. This molten caramel peanut mixture is then carefully poured over the waiting sheet of nougat, spreading in a thick, warm blanket. Machines equipped with adjustable blades ensure even coverage and exact thickness. The two layers now fuse gently together, forming the recognizable base structure of a Snickers bar. As the combined sheet moves along the conveyor, it enters a cooling tunnel, a long chamber filled with chilled, dry air that gradually firms the caramel without making it brittle. The transition from warm to cool must be gradual to prevent cracking or separation between layers. When the sheet emerges from the cooling tunnel, it's firm enough to cut. Precision slices move in synchronized lines, dividing the wide sheet into individual bar-width strips, and then again into the familiar rectangular lengths. Each bar now looks like a naked Snickers, the inside exposed, showing its layered cross-section of nougat, caramel, and peanuts. But the most recognizable part still lies ahead, the coating of milk chocolate that seals it all together. The chocolate coating process is mesmerizing. The cut bars travel along a narrow conveyor and enter an enrober, a tunnel-like machine where liquid chocolate flows continuously like a curtain. As the bars pass beneath, they're drenched in smooth, glossy chocolate that coats every side. The excess drains away through a vibrating mesh, leaving a perfectly even layer. The smell is intoxicating, cocoa-rich and creamy, filling the air with warmth. To prevent bubbles or streaks, the enrobed bars are lightly air-blown and then guided into another cooling tunnel. Inside, the temperature is carefully controlled so that the chocolate sets gradually, forming that signature, soft but firm shell that melts at body temperature. When they emerge, the Snickers bars are fully formed, shiny, smooth, and unmistakably themselves. But the work isn't done yet. Each bar passes through a gauntlet of sensors, cameras, and metal detectors that ensure no foreign objects or defects are present. Any bar that's misshapen, unevenly coated, or slightly off in weight is automatically diverted off the line. The rest continue toward the wrapping machines. Packaging is its own marvel of synchronization. Thousands of foil and plastic wrappers are fed through rollers, cut, printed, and sealed at breathtaking speed. Each Snickers bar slips neatly into its wrapper, the ends crimped shut with heat and pressure. Then the bars are grouped, boxed, and stacked onto pallets. The rhythmic hiss of sealing, the click of rollers, and the hum of conveyors fill the packaging area like a mechanical orchestra. From here, the boxes are labeled and shipped out to warehouses ready to travel to every corner of the world. In a single large plant, millions of bars can be made in a day, yet every one of them must taste identical, the same balance of sweet, salty, nutty, and chocolatey. Achieving that consistency requires not only automation, but an intricate understanding of food chemistry. The caramel must stay soft even after months of storage. The peanuts must retain crunch despite being embedded in moisture-prone caramel. The chocolate coating must stay glossy and stable across different climates. To accomplish this, scientists test formulations constantly, adjusting ratios and refining ingredients. Even the thickness of the chocolate shell is calibrated by micrometers. Temperature control defines every step of the process. From the moment sugar is melted to the instant the chocolate cools, precision matters. A shift of just a few degrees can change texture and flavor. The nougat must stay aerated, the caramel must remain elastic, and the chocolate must crystallize into its ideal form, a process called tempering. In modern Snickers factories, these variables are monitored by computer systems that log data in real time, allowing operators to see graphs of viscosity, flow rates, and cooling curves as the bars move down the line. It's as much a scientific laboratory as a kitchen. And yet, despite all this engineering, there's something undeniably human in the candy's appeal. The flavor combination feels instinctive. Salt, fat, sugar, crunch. A sensory symphony designed to satisfy almost every craving. A single bite gives way to texture shifts. First the snap of chocolate, then the chew of caramel, the crumble of nougat, the crunch of peanuts, and the slow melt of sweetness that follows. That balance is deliberate. Every layer crafted to engage a different part of the palate. As the day winds down in the factory, the machines are cleaned, their surfaces gleaming under fluorescent light. Workers hose away traces of caramel and sweep up stray peanuts from the floor. The air still smells faintly of chocolate and roasted nuts, a scent that lingers long after production stops. Rows of freshly boxed Snickers bars sit stacked and ready, each identical to the last, each a small testament to the precision and passion behind something so familiar. It all begins with the careful sourcing and intake of raw chicken, a process that is both biologically sensitive and highly mechanized to maintain consistent quality and food safety. The chickens destined for KFC facilities are selected from specific poultry farms that follow stringent guidelines set by both KFC's corporate standards and local regulatory bodies. These farms raise broiler chickens, a breed specifically developed for rapid growth and high meat yield, particularly in the breast and thigh areas. To ensure consistency in texture and flavor, the birds are typically grown under controlled feeding regimens with strict monitoring of their diet, environment, and health status from hatchery to harvest. Once the birds reach the appropriate weight and age, usually between 5 to 7 weeks, they are transported live in temperature-regulated, well-ventilated trucks to the processing facility. Upon arrival, the birds are unloaded through an automated conveyor system and transferred to a staging area that uses dim lighting and gentle sound cues to keep the animals calm. This pre-processing environment is crucial for maintaining meat quality, as high stress can cause conditions like pale, soft, and exudative meat, or dark, firm, dry meat, which are both unsuitable for KFC's strict quality requirements. The first critical step in the factory is stunning, which is done using controlled atmosphere stunning, a method that introduces carbon dioxide in gradually increasing concentrations to render the chickens unconscious. This technique is widely considered more humane and helps preserve the quality of the meat. Once the birds are unconscious, they move to the next stage, where an automated system makes a precise incision to the neck, ensuring rapid and thorough bleeding. The bleeding process is closely timed and monitored using sensors and timers to maximize the efficiency of blood removal, which is essential not only for meat appearance and shelf life, but also for meeting food safety regulations. Following exsanguination, the birds proceed through a high-capacity scalding tank filled with water heated to approximately 60 degrees Celsius. This stage loosens the feathers by relaxing the collagen in the feather follicles. The duration and temperature are controlled to a fine margin to ensure that the skin is neither overcooked nor damaged. After scalding, the birds are transferred into rotary feather pluckers, drum-shaped machines lined with soft rubber fingers that rotate at high speeds. These fingers remove feathers through a gentle abrasive action. Any residual feathers, particularly around the wings and tail, are removed by additional targeted plucking devices or hand finishing stations, depending on the processing line speed and factory setup. The next step is evisceration, a highly mechanized process involving robotic arms and vision-guided machinery. The system first makes a precise incision along the abdominal cavity before extracting the internal organs. This includes the heart, liver, gizzard, and intestines, which are separated into byproduct streams for different uses or disposal. Each carcass is inspected by high-speed cameras equipped with AI-powered image recognition software to detect any abnormalities such as bruising, discoloration, or contamination. Chickens that fail this inspection are automatically diverted from the production line for further examination or removal. This real-time quality assurance technology helps maintain a consistent and safe supply of chicken for further processing. Now it's time to move on to the chilling process, which is absolutely vital for halting bacterial growth and ensuring a clean transition from slaughter to further cutting and seasoning. KFC factories typically use an immersion chilling method, where eviscerated chickens are conveyed through long stainless steel tanks filled with chlorinated cold water, maintained at around 0 to 4 degrees Celsius. The flow of water is designed in a countercurrent pattern, meaning the cleanest water contacts the most recently added chickens, ensuring optimal hygiene. This step rapidly reduces the internal temperature of the chicken from roughly 40 degrees Celsius to below 4 degrees within an hour, thereby locking in freshness and significantly extending the shelf life of the meat. After chilling, the carcasses proceed to the cutting and portioning stage. This part of the process is perhaps one of the most intricate in the factory. Specialized rotary cutting machines equipped with lasers and 3D scanners assess the size and density of each chicken in real time. Based on this data, programmable robotic blades segment the carcasses into uniform cuts: legs, thighs, wings, breasts, and keels. Each piece is sized to match strict dimensional and weight criteria, which are crucial for ensuring consistent cooking times and presentation across all KFC restaurants worldwide. The system is calibrated to yield the optimal number of each type of piece from every bird, reducing waste and maximizing efficiency. If a cut doesn't meet the precise size range, it is automatically redirected for use in alternative products like tenders or popcorn chicken. The next phase focuses on marination, a process that introduces moisture, flavor, and functional ingredients into the chicken to enhance both taste and texture. Once portioned, the chicken pieces are loaded into massive stainless steel tumblers, each capable of holding hundreds of kilograms of product. Inside the tumbler, a proprietary liquid marinade blend is introduced. While the exact formulation is a closely guarded secret, the marinade typically includes salt, phosphate-based tenderizers, flavoring agents, and sometimes buttermilk solids to create the tender, juicy interior that KFC is known for. The tumbling action lasts anywhere from 15 to 30 minutes, depending on the batch size and desired intensity, and the drum rotates on multiple axes to ensure that every surface of every piece of chicken is exposed to the marinade. This mechanical agitation also helps the meat fibers absorb the liquid more thoroughly, contributing to the product's juiciness even after high temperature frying. But up next comes the breading stage, which is arguably the most iconic part of KFC's production process. After marination, the chicken is gently drained and transferred to the breading stations, where each piece is coated in the proprietary blend of flour and seasoning known famously as the 11 herbs and spices. To replicate the hand-breaded quality that KFC is known for, even at industrial scale, specialized breading drums are used. These drums simulate the hand-tossing action by gently rolling the chicken pieces in the seasoned flour, while pneumatic paddles and vibration systems ensure that every crevice is fully coated. At this point, moisture content is carefully controlled to ensure adhesion without creating clumps or overly moist surfaces, which would ruin the crispy texture during frying. Once breaded, the chicken moves immediately to the par-frying or pre-frying stage. This step is critical for setting the breading so it doesn't fall off during full cooking at the restaurant. The breaded pieces are passed through continuous fryers filled with hot oil maintained at temperatures between 170 to 180 degrees Celsius. In this stage, the chicken is fried for a short duration, usually 90 to 120 seconds, just enough to solidify the coating and begin the Maillard reaction, which is responsible for the development of flavor and the golden color. The oil used in this step is filtered and refreshed continuously using an inline oil management system that maintains optimal frying conditions and ensures that the final product is never tainted by burnt residues or off flavors. The partially cooked chicken is then lifted out of the fryer via a conveyor system and deposited onto a draining belt that uses both gravity and air jets to remove excess oil. Now, it's time to transition to the flash freezing process. This is where partially cooked chicken is rapidly frozen to lock in all the flavors, textures, and moisture absorbed during marination and breading. Each piece is conveyed into a spiral freezer or impingement freezer, both of which use sub-zero air blasts or liquid nitrogen vapor to drop the temperature of the chicken from over 60 degrees Celsius to below -18 degrees in under 10 minutes. Rapid freezing is crucial to prevent the formation of large ice crystals, which can damage the cellular structure of the meat and result in dryness or texture loss after final cooking. During this process, each piece is also individually quick frozen, which prevents clumping and allows for precise portioning when packaging. The next step in the factory process is the automated packaging of the individually quick frozen, par-fried chicken pieces, a phase that combines high-speed precision machinery with meticulous control over product integrity. Once the chicken emerges from the spiral or impingement freezer, Each piece is conveyed to a sophisticated vision inspection system that performs a final quality assurance check. High-resolution cameras and laser scanners examine each piece for uniform breading coverage, appropriate size, and the absence of any structural defects like broken bones or irregular shapes. Pieces that fail this inspection are removed from the line using targeted air jets and routed for rework or disposal, depending on factory protocol. Once the pieces pass inspection, they are conveyed into a portioning station where intelligent weighing and sorting systems group them into standardized sets that align with KFC's iconic bucket meal configurations. These could be 8-piece, 12-piece, or 16-piece configurations, depending on the regional product lineup. Multi-head weighing machines calculate the total weight and count of each portion, ensuring that every pack not only meets visual and compositional standards, but also falls within a narrowly defined weight range for inventory accuracy and consistent customer experience. These grouping systems operate at incredibly high speeds, hundreds of portions per minute, with tolerances as tight as +1 gram. Each portion of chicken pieces is then dropped into a form-fill seal machine or into pre-formed plastic pouches, depending on the final packaging format. The form-fill seal machines shape a plastic film into a bag, load it with chicken, flush it with a nitrogen-rich gas to minimize oxygen, and heat seal it in a continuous, uninterrupted process. Modified atmosphere packaging is used here to extend shelf life while preventing freezer burn or flavor degradation. The gas blend, often a mix of nitrogen and carbon dioxide, inhibits microbial growth and oxidation without adding any chemicals or preservatives. After sealing, the packages are labeled with all necessary tracking and compliance information. High-speed thermal transfer printers apply labels that contain lot numbers, plant codes, production timestamps, and freeze dates. These labels also include data matrix barcodes or QR codes used for traceability, allowing KFC's central quality control teams to trace every package back to its exact farm, batch, and processing line in the event of a recall or audit. Automated verification systems scan each label for accuracy and readability. Any incorrectly labeled packages are automatically rejected from the line and placed in a designated review bin for manual inspection. Now it's time to move on to case packing, where multiple individually sealed packs of chicken are grouped into corrugated cardboard boxes, each built to withstand long-distance cold chain transportation. Robotic arms equipped with vacuum suction grippers pick and place the sealed bags into the boxes with extreme precision, ensuring that space is maximized while maintaining the integrity of the chicken. Each case typically holds a specific number of meals or bucket configurations and is marked with a unique identifier. Once filled, the boxes are sealed using automated taping machines and pass through weight verification stations to ensure each box matches the expected load. Once packed, these boxes are stacked onto pallets using robotic palletizers. These robots follow pre-programmed stacking patterns that balance weight and maximize vertical space without compromising stability. Slip sheets and corner boards are often inserted between layers to protect the boxes during transit. Each completed pallet is then shrink wrapped using a rotary arm or turntable stretch wrapper, which encases the entire stack in several layers of industrial plastic film to secure the load for transportation. A final barcode label is applied to each pallet, integrating it into the warehouse management system, which tracks every movement of inventory from production to dispatch. Next comes the crucial cold storage phase. The finished pallets are transferred via automated guided vehicles or high-speed conveyor systems into a massive cold storage facility, maintained at a consistent temperature of -18 degrees Celsius or lower. These storage facilities are designed with energy efficiency and inventory management in mind, often featuring high bay racking systems and vertical lift modules that allow for dense, organized storage. Temperature and humidity are monitored continuously by sensors linked to a centralized control room, where technicians receive alerts if any deviations occur. These warehouses are often equipped with backup generators and emergency protocols to ensure uninterrupted refrigeration in the event of power failures. After sufficient time in cold storage, which may range from a few days to several weeks depending on demand, the frozen chicken pallets are scheduled for distribution. The dispatch process begins with a pick and pack phase, where orders from various KFC regional hubs or franchise warehouses are collated. Advanced logistics software optimizes which pallets to pull based on freshness, production date, and delivery location. Selected pallets are loaded onto refrigerated trailers that maintain a controlled environment throughout the entire journey. These trucks use insulated walls and powerful refrigeration units that can be monitored remotely to ensure temperature compliance from factory to franchise. As these trucks transport the frozen chicken to regional KFC distribution centers or directly to individual restaurants, the cold chain is never broken. The receiving locations are equipped with cold storage facilities of their own, ensuring the chicken remains at safe temperatures until it's needed. At this stage, each restaurant receives a specific allocation based on forecasted customer demand, which is calculated using advanced demand planning software linked to point-of-sale data and regional market trends. The chicken remains sealed until it's ready to be used in the restaurant's kitchen, where the final stages of cooking take place. But now it's time to dive into the heart of the KFC restaurant kitchen, where the transformation from pre-cooked frozen chicken into the hot, crispy, golden brown pieces we all recognize occurs. After thawing in temperature-controlled refrigeration units for a specific number of hours, typically overnight, the chicken is brought to the breading station. Though the chicken was par-fried and breaded at the factory, a second layer of fresh breading is applied in-store to create the distinctive double crunch texture KFC is famous for. This is where the Colonel's proprietary 11 herbs and spices come into play. Each restaurant receives sealed tubs of this secret seasoning blend, pre-measured and tamper-proof. The thawed chicken pieces are first dipped into a cold, seasoned egg wash or a specialized batter mix, depending on the region. Then, they are placed into large breading bins containing the flour and spice mixture. Trained team members follow a specific press and fold technique, which involves pressing the flour onto the surface of the chicken and folding it multiple times to ensure full adhesion and the formation of the characteristic craggy, crispy coating. Each piece is then gently shaken to remove excess breading and laid out on wire racks to rest before frying. This resting period is short but essential. It allows the coating to set and adhere to the surface of the meat, reducing slippage during frying. Next, the chicken is placed into large open fryers filled with high stability frying oil, often a soybean or canola blend, optimized for high temperatures and neutral taste. The fryers are preheated to exact temperatures, typically around 170 to 180 degrees Celsius, and the chicken is cooked under pressure for a controlled duration. KFC's use of pressure fryers is a distinctive element of its cooking process. The pressure cooking not only reduces cooking time, but also seals in moisture, ensuring the chicken remains juicy while achieving a perfectly crispy exterior. Sensors inside the fryer monitor oil temperature, pressure levels, and cooking duration down to the second. Once the timer signals completion, the fryer basket lifts automatically and the cooked chicken is removed using heat-safe tools to ensure safety and hygiene. After frying, the chicken is transferred to heated holding cabinets that maintain a precise internal temperature, typically around 60 to 65 degrees Celsius, for a limited time, usually no longer than 90 minutes, to ensure optimal freshness and food safety. These cabinets are fitted with internal timers and alert systems to prompt kitchen staff when a batch is nearing the end of its holding time. Any product not sold within this window is discarded according to food safety protocols to maintain KFC standards. Now that the chicken is hot, crisp, and ready, it's portioned into the familiar red and white striped buckets. Each bucket is made from food-grade, grease-resistant cardboard, printed with high-resolution branding that remains vibrant, even under heat and oil exposure. The buckets are assembled on-site from flat pack form using pop and lock mechanisms, and lined with waxed paper liners. The kitchen crew follows strict guidelines when arranging the pieces inside each bucket, ensuring an appealing visual mix of drums, thighs, wings, and breasts. The buckets are then sealed with fitted plastic or cardboard lids to retain heat and are either handed to walk-in customers or packed into thermal delivery bags for transport. The final stretch of the production process involves a complex web of quality assurance protocols, food safety audits, sustainability initiatives, and continual technological improvements, all of which are critical to ensuring that every KFC fried chicken bucket, whether purchased in Tokyo, New York, or Johannesburg, meets the same high standard of taste, appearance, and food safety. These behind-the-scenes systems may not be visible to the end consumer, but they represent the foundation of KFC's global manufacturing and supply chain model. One of the most rigorous systems in place is the Hazard Analysis and Critical Control Points, or HACCP, framework. This is applied across all phases of the production lifecycle, from live animal handling at the poultry farms to final packaging at the restaurant level. Every critical control point is identified, monitored, and logged digitally. For example, in the chilling process, sensors verify that the internal temperature of chicken pieces drops to below 4 degrees Celsius within a very specific time frame. If any batch fails to meet that requirement, the system will automatically flag the anomaly, prevent further processing, and isolate the affected lot until a manual inspection is completed. These digital controls are complemented by human oversight. Trained quality control technicians regularly inspect samples at random, visually assessing breeding adhesion, meat color, texture, and aroma. At the plant level, sanitation is treated as a mission-critical activity. Every line, blade, and conveyor is cleaned on a strict schedule using a validated multi-step process that includes rinsing, application of food-grade alkaline and acidic detergents, hot water sanitizing, and ATP testing to detect any microbial residues. Cleaning in place systems are used in closed-loop systems like marinade blenders and oil filtration units, ensuring deep sanitation without the need for dismantling complex machinery. Swabs are taken from surfaces and air samples collected to detect airborne pathogens, all analyzed in on-site microbiological labs. If even a trace of Listeria, Salmonella, or E. coli is detected, entire zones of the plant are shut down and sanitized before production can resume. In parallel to these food safety systems, sensory panels and culinary scientists at centralized R&D hubs conduct organoleptic tests to ensure product consistency. These tests assess everything from the crunch of the breading to the juiciness of the meat and the aroma released when the bucket is first opened. Chicken from multiple plants is cooked and compared side by side in blind taste tests to identify deviations in flavor or texture. If a factory's output strays from the baseline profile, its formulations and techniques are reviewed. In some cases, regional adaptations are permitted. For instance, a slightly spicier breading formula in Southeast Asia, or a less salty blend in Scandinavian markets. But these must be approved through corporate sensory panels and extensive pilot runs. Now it's time to take a look at how traceability and supply chain visibility are achieved at scale. Every piece of chicken can be traced through a blockchain-based system that logs data from farm to fryer. RFID tags and barcode labels track each pallet, batch, and case throughout its journey. When a truck departs a cold storage warehouse, its GPS location is monitored in real time, and its refrigeration status is transmitted back to the operations center every 5 minutes. If a delivery truck's temperature rises above the acceptable range for more than 10 minutes, alerts are sent automatically, and corrective actions are triggered, either rerouting to a nearby cold facility or discarding the load, depending on the severity of the excursion. Once the product reaches the restaurant, the store-level staff become the final link in the quality chain. Every team member is trained not just in food preparation, but in safe handling and equipment calibration. They measure oil temperatures with infrared thermometers before every cooking cycle, check holding cabinet thermostats each hour, and perform timed inventory rotations to prevent expired stock from being used. Any discrepancies are flagged in a digital checklist that is reviewed daily by shift supervisors and weekly by regional managers. Corporate auditors also perform unannounced inspections using checklists derived from international food safety certifications such as ISO 22000 and BRC Global Standards. But up next is a growing area of emphasis for KFC's manufacturing process, sustainability. As environmental concerns increasingly shape consumer expectations and regulatory policy, KFC and its supply chain partners have invested heavily in reducing their environmental impact without compromising efficiency or food safety. For instance, many factories now operate on hybrid energy models that integrate solar or wind power into the grid supply. Heat exchangers capture and recycle waste heat from fryers and ovens to preheat water for cleaning cycles. Water treatment plants have been installed adjacent to major facilities to purify and reuse water from scalding tanks and chilling baths, thereby reducing freshwater consumption by up to 60%. Waste management is another cornerstone of sustainable operations. Offcuts, bones, and organ meats removed during the evisceration process are rendered into protein meal for use in animal feed or fertilizer. Oil used during the par frying phase is filtered multiple times and eventually recycled through third-party processes into biodiesel or industrial lubricants. Even the breading flour that falls off during coating is collected, sifted, and reused within the same batch cycle if it remains uncontaminated thanks to high-speed sifters and air classification systems. Packaging materials are continuously redesigned to reduce plastic use, and many regional markets have adopted compostable or recyclable buckets made from sugarcane fiber or recycled cardboard. Now let's touch on automation and the future of food manufacturing. KFC's supply chain continues to push the boundaries of factory automation. Smart robotics now handle everything from chicken loading and cutting to box folding and pallet stacking. Machine learning algorithms analyze yield patterns, worker performance, and maintenance schedules to optimize output while minimizing downtime. Vision systems are paired with artificial intelligence to assess product quality in real time, not just based on weight and shape, but also by identifying anomalies invisible to the human eye, such as microfractures or uneven breading density. One of the most promising developments is the integration of digital twins, virtual replicas of entire production lines that allow engineers to test modifications in real time before applying them in physical factories. If a new breeding formula is under development, it can be modeled digitally to predict how it will behave under tumbling, par frying, and freezing conditions. These simulations save weeks of trial and error testing and reduce waste. Some facilities even employ predictive maintenance systems powered by sensors embedded in critical equipment. These sensors monitor vibration, temperature, and pressure, allowing for preemptive repairs before machinery fails, ensuring smooth operations and uninterrupted chicken production. KFC has also begun exploring vertical integration of its logistics chain. In some regions, specially designed micro-factories are situated closer to major urban centers, reducing transit time and carbon emissions. These micro-factories handle final stage breading and par frying, enabling fresher product delivery and enhanced responsiveness to demand fluctuations. Combined with real-time sales analytics from thousands of KFC restaurants, these decentralized production nodes can respond dynamically, ramping up or down based on foot traffic, promotions, or seasonality. The production of Cheetos begins not with cheese or seasoning, but with one humble ingredient: corn. In fact, the specific type of corn used in Cheetos manufacturing is carefully selected and processed to meet exacting technical standards before it even enters the plant. The base product of every Cheeto is degermed cornmeal, derived from a variety of field corn that is specially cultivated for its high starch content and low fat levels. This corn must produce a uniform, predictable puff when subjected to extreme heat and pressure, so its density, moisture content, and kernel hardness are closely monitored even at the agricultural stage. Farmers contracted by the manufacturer are required to meet tight tolerances in grain quality, harvesting methods, and post-harvest drying to ensure the raw corn will meet the standards for industrial puffed snack production. Once harvested and transported to the ingredient supplier, the corn undergoes an initial cleaning to remove plant debris, soil, and foreign materials. It is then taken through a degermination process, in which the outer bran layer and the germ, the oil-rich, nutrient-dense part of the corn kernel, are removed. This step is essential. While germ and bran contain healthy fats and proteins, their presence can negatively impact the expansion properties and shelf life of the final product. Germ oil can go rancid over time and interfere with the consistent puff structure that defines a Cheeto. What remains after degermination is the starchy endosperm, milled down into a fine cornmeal that becomes the building block of every puff. This cornmeal is then enriched with a blend of vitamins and minerals, including riboflavin, niacin, iron, and folic acid. The enrichment not only helps meet nutritional labeling requirements, but also contributes to uniformity in the extrusion process, as these additives influence how the mixture reacts under heat and pressure. The resulting product is a dry, golden yellow flour with a specific granulation profile tailored to the plant's extrusion parameters. Before it is used on the production line, the cornmeal is stored in temperature and humidity-controlled silos directly connected to the processing plant. These silos often hold hundreds of metric tons of product and are designed to keep the cornmeal in a stable state for extended periods. Pneumatic systems transfer the cornmeal through stainless steel pipelines to weigh hoppers on the factory floor, where batch sizes are precisely measured. Real-time inventory sensors track the flow of material and communicate with the factory's central control system to automatically replenish supply lines as needed, ensuring uninterrupted production. Now it's time for the first transformation phase, hydration and preconditioning. The cornmeal is metered into a continuous mixing system where it is blended with water or steam to raise its moisture content to a narrowly specified range, usually between 15% and 20%. This step is essential to prepare the starch molecules for gelatinization. The equipment used here is not unlike a ribbon blender or paddle mixer, which agitates the mixture thoroughly to ensure every granule of cornmeal is evenly hydrated. Water is introduced through atomizing nozzles positioned at calculated intervals along the mixer's length, and multiple moisture sensors along the pathway feed back to the PLC system to adjust water input in real time. This moist mixture, often referred to as dough, despite its loose, crumbly texture, is held briefly in a conditioning tank to allow for even moisture distribution. The temperature and residence time are carefully controlled. If the mix is too hot or too wet, it may pre-gelatinize and clog the extruder. Too dry, and it won't expand properly. During this stage, the product is slowly moved along a jacketed screw conveyor that maintains a consistent temperature and prevents clumping. Now we arrive at the heart of the production line, the extruder. Industrial Cheetos are made using a twin screw extruder, one of the most sophisticated and critical machines in the plant. The twin screw configuration allows for highly controlled processing of the corn mixture, providing better mixing, higher shear, and superior control over temperature and pressure compared to single screw models. The hydrated cornmeal is fed into the extruder barrel, where it encounters two rotating screws that convey the material forward under intense mechanical pressure. External heaters line the barrel and raise the temperature incrementally as the product moves through each zone. Inside, shear forces generated by the screws convert some of this mechanical energy into heat, further increasing the temperature of the dough. The intense conditions inside the extruder pressure in the range of 200 to 500 psi and temperatures from 130 degrees Celsius to 180 degrees Celsius cause the starches in the cornmeal to gelatinize and the water to superheat. The dough undergoes plasticization, becoming a molten mass under pressure. As this molten dough reaches the end of the barrel, it is forced through a die, the precision-crafted metal plate that defines the shape of the puff. The die hole is round and small, but as the dough exits into atmospheric pressure, the superheated water in the mixture flashes into steam, causing the structure to puff and expand dramatically in a fraction of a second. This rapid expansion is responsible for the iconic airy texture of a Cheeto. Just outside the die, rotating knives spin at high speed, slicing the continuous stream of puff into uniformly sized segments. The speed of the knives determines the length of the puff, while the pressure and temperature within the extruder affect its diameter and density. But even after this high-tech transformation, the newly extruded Cheetos are far from finished. They are still pale, moist, and bland, essentially unseasoned corn puffs. The next stage is all about turning them into the crunchy, craveable snack that consumers instantly recognize. First, the extruded pieces are conveyed via vibrating trays to a frying system. Here, they're submerged in hot oil, typically corn or canola oil, at carefully controlled temperatures ranging between 160 degrees Celsius and 180 degrees Celsius. The residence time in the fryer is only about 20 to 40 seconds, but in that time, the moisture content is reduced dramatically from around 15% to under 2%. This not only creates the final crispy texture, but also deepens the color slightly, giving the snack its characteristic golden hue. The fryer itself is a marvel of engineering, equipped with multiple sensors and filtration systems. Oil turnover rates are high, meaning that fresh oil is constantly added, while spent oil is removed and filtered to maintain quality. Skimmers remove any floating particles, and oil chemistry is monitored for signs of oxidation, free fatty acid levels, and polymerization. If any readings fall outside of the strict parameters, the fryer automatically triggers corrective actions, dosing with fresh oil, increasing filtration, or even pausing the line to prevent compromised batches from continuing downstream. After exiting the fryer, the Cheetos are carried on mesh conveyors through an air cooling tunnel. High-powered fans blow ambient or conditioned air over the freshly fried snacks, bringing them to a safe handling temperature and ensuring any surface oil solidifies just slightly to help the seasoning adhere. These cooling conveyors are extended and designed with soft vibratory motion to prevent breakage, ensuring that the delicate puffs remain intact before entering the seasoning phase. Next, the Cheetos are transferred into a massive rotating flavor drum, where their bland exterior is transformed by a shower of powdered cheese blend. But before we dive into the complexities of seasoning, we'll need to explore how oil coating is applied for adhesion and how powder distribution systems are calibrated to ensure every single puff gets the perfect amount of flavoring. This next part of the production process is where precision meets sensory science, and the result is the addictively cheesy snack that has become a global favorite. Now it's time to dive into one of the most iconic and intricate stages in Cheetos manufacturing, the flavoring phase. This is where the bland, puffed, and fried corn kernels are transformed into the intensely savory, cheese-coated snacks recognized all over the world. The process of seasoning Cheetos is not merely about tossing on a bit of cheese powder. It is an engineered, tightly controlled operation that determines product consistency, taste balance, visual appeal, and even mouthfeel. Everything from the size and porosity of the puff to the electrostatic charge of the powder particles is taken into account in this phase. After exiting the cooling conveyor from the fryer, the puffs are transferred into large rotating cylindrical drums called flavor tumblers. These drums are typically positioned on a gentle incline and rotate slowly. creating a continuous cascade of puffs inside the drum that exposes every surface area of each piece as they tumble forward. This mechanical tumbling is crucial. It ensures an even coating without crushing the fragile, aerated product. Inside the drum, two key applications occur almost simultaneously. First, a fine mist of oil is sprayed onto the hot puffs. Then, a controlled stream of seasoning powder is dispensed over the tumbling mass. The oil, which is typically a neutral vegetable oil like corn or canola, plays several roles in this step. Primarily, it acts as an adhesive layer that allows the seasoning powder to stick effectively to the puff's surface. Additionally, it helps activate the flavor compounds in the powder blend, carrying volatile aroma molecules and enhancing taste perception. The oil spray system uses ultra-fine atomizing nozzles that are precisely calibrated to deliver a uniform coat without oversaturation. Too much oil, and the puffs become greasy and soggy. Too little, and the powder won't adhere properly, leading to uneven seasoning distribution and flavorless bites. The timing, angle, and rate of oil application are closely monitored and adjusted by sensors and programmable logic controllers. Real-time feedback systems measure oil usage, droplet size, and the thermal signature of the puffs to ensure that coating is optimal under varying production speeds or ambient conditions. This level of automation ensures consistency across thousands of pounds of product produced per hour. As the puffs are coated in oil, the seasoning powder is introduced using a vibratory feeder or screw conveyor system. The powder is held in a hopper mounted above the flavor drum and is dispensed through controlled openings at a fixed rate, matched to the flow of puffs. The exact dosing rate depends on the type of Cheetos being produced. Flamin' Hot varieties require slightly more powder per unit than the traditional cheese puffs due to differences in density, powder, granularity, and flavor intensity. The seasoning blend itself is a complex formulation engineered not only for taste, but also for flow characteristics, adhesion, and shelf stability. The base of the powder is often dehydrated cheddar cheese, spray-dried into a fine particle form. This is combined with whey or whey protein concentrate, maltodextrin, salt, monosodium glutamate, MSG, disodium phosphate, citric acid, and natural or artificial flavors. Each of these ingredients plays a very specific role. Maltodextrin, for example, acts as a carrier and anti-caking agent that helps the powder distribute evenly and resist clumping. Citric acid provides a tangy bite that enhances cheese flavor. MSG boosts umami and deepens savory perception. Color additives like annatto or oleoresin paprika for classic cheese, and red 40 or yellow 6 for Flamin' Hot are oil dispersible pigments that give the snack its vivid appearance without creating spotting or streaks. The particle size distribution of the powder is engineered to align with the surface texture of the puffed snack. Powder that's too coarse will fall off, and powder that's too fine will clump or create an overly dusty texture. To prevent powder fallout, electrostatic systems are sometimes used in high-speed lines. In these cases, the powder is given a minor static charge to improve its affinity for the puff surface, minimizing waste and improving adhesion. Inside the flavor tumbler, the balance of oil spray and powder distribution creates a beautiful, uniform layer of seasoning that fully coats each puff without pooling at the bottom of the drum or leaving bald spots on the product. The drum's internal design is key. Angled baffles gently lift and drop the puffs to keep them moving without subjecting them to mechanical stress. As the snacks make their way to the end of the drum, they are now visually and sensorially transformed. Bright orange, evenly coated, and bursting with aroma. Once the seasoning phase is complete, the fully flavored Cheetos are gently transitioned to the final conveyor belt systems that lead to the packaging area. Here, another series of quality control measures come into play. Inline camera systems inspect color uniformity and powder coverage using advanced image recognition algorithms. If a section of the product stream is detected to have an irregular appearance, whether due to light seasoning, overcoating, or discoloration, it is flagged and diverted from the main line for manual inspection or disposal. At this point, the Cheetos are still vulnerable to moisture pickup, oxidation, and mechanical damage, so the packaging process must move swiftly and with precision. The conveyor system delivers the finished puffs to a multi-head weigher mounted above the bagging machines. This machine uses multiple weigh hoppers to rapidly measure exact product portions, typically in the range of 28 g to 250 g per serving, depending on the bag size. These weighers use real-time load cell feedback to select the optimal combination of buckets to match the target weight, within a tolerance as tight as +2g. Each pre-measured portion is released down a chute into a vertical form-fill seal (VFFS) machine. These machines work by pulling a flat roll of pre-printed film through a collar that forms it into a tube. The bottom of the tube is heat sealed to create the first seam, the Cheetos are dropped in, and then the top is sealed and cut, simultaneously forming the bottom seal of the next bag in line. These machines can fill and seal over 100 bags per minute per lane, and multiple lanes often run in parallel for large-scale production. The film used for the packaging is multi-layered and engineered to provide barrier protection against light, oxygen, and moisture. It typically includes an outer polyester film for print quality and visual appeal, a middle layer of aluminum or metallized polypropylene for oxygen and light resistance, and an inner polyethylene layer for heat sealing and moisture resistance. As each bag is sealed, a date code, batch number, and factory identifier are printed using high-speed inkjet printers for traceability. Just after sealing, every bag passes through a series of checkpoints. Metal detectors scan for any foreign objects, vision systems verify print alignment and code readability, and weight checkers ensure compliance with regulatory standards. Non-conforming bags are automatically ejected onto a rejection conveyor, where they are set aside for manual inspection. Approved bags are then grouped and packed into cardboard shipping cartons by robotic pick-and-place systems or automated drop packers. These cartons are sealed, barcoded, and routed to the palletizing station. Here, industrial robotic arms stack the cartons onto wooden or plastic pallets using optimized patterns for stability and load balance. As each pallet is completed, it is wrapped in stretch film to secure the load and protect it from dust and humidity during storage and transportation. The palletized loads are then scanned into the plant's warehouse management system, which tracks location, batch status, and distribution destination. Some pallets are moved to ambient storage if they are designated for short-haul routes, while others are transported to climate-controlled storage areas that maintain low humidity and consistent temperatures, ensuring that the product maintains its texture and flavor until it reaches its final destination. What follows is the outbound logistics phase, where the pallets are loaded onto trucks, routed to distribution centers, and delivered to retailers. But for now, every step inside the production facility, from the moment the cornmeal is hydrated to the final bag, passing the last inspection point, has been a meticulously engineered series of chemical, mechanical, and sensory transformations. Every component of the Cheetos production line is designed not just for efficiency and speed, but to deliver a reliably indulgent experience in every bag. And it all happens in a continuous, automated, high-output environment that must maintain exacting standards of quality, cleanliness, and consistency hour after hour, shift after shift. One of the key operational pillars at this stage is environmental control. Temperature, humidity, and airflow within the production zones are tightly monitored and controlled around the clock. Cheetos, especially after frying and seasoning, are highly sensitive to ambient conditions. If the air in the seasoning or packaging area carries too much humidity, for instance, the cheese powder may begin to clump, reducing its dispersibility and leading to uneven coating. Worse still, excess moisture can cause the puffs to begin absorbing water from the air, softening the texture and compromising the crisp, dry bite expected by consumers. To prevent these issues, HVAC systems specifically engineered for food processing environments are deployed throughout the Cheetos plant. These systems do more than just heat or cool. They dehumidify, filter, and exchange the air in sensitive zones at rapid intervals, ensuring a constant flow of purified, dry, temperature-stabilized air. Some areas, such as the seasoning tumblers or the vertical form-fill seal zone, may be isolated with positive air pressure to ensure that external air, dust, and contaminants do not seep into these critical zones. These environmental systems are integrated with digital controls that feed data into the facility's central monitoring hub. Temperature and humidity data are tracked every few seconds, and if any reading moves outside of pre-programmed tolerances, automatic alarms notify technicians to investigate immediately. In some cases, the system will even halt upstream processes automatically to prevent production under unsuitable conditions, protecting product quality. While environmental controls maintain external conditions, another system ensures the quality of what's happening on the line, inline quality assurance, and real-time analytics. Throughout the Cheetos line, from extrusion to bagging, dozens of sensors, scanners, and cameras work in unison to gather data on key quality metrics. These include moisture content, oil absorption rate, puff size, color uniformity, seasoning coverage, and weight per unit. Each of these factors contributes not only to taste and mouthfeel, but to customer satisfaction and regulatory compliance. Advanced laser micrometers and stereo imaging cameras measure the dimensions of each puff as it moves across the line at high speed. If puffs fall outside the programmed size range, either due to inconsistent extrusion pressure, die blockage, or improper cutting, those units are flagged and rejected automatically using pneumatic diverting arms. Simultaneously, optical sensors inspect the color of the fried puff to confirm it matches brand-specific targets. Color variation could indicate improper frying time, fluctuating oil temperature, or oil degradation. The system will trigger alerts or shut down sections of the line if it detects drift from acceptable limits. Another important part of inline quality is the metal detection system. Every snack must pass through high-sensitivity metal detectors or, in some cases, X-ray systems just before packaging. These devices scan for trace amounts of ferrous, non-ferrous, and stainless steel contaminants which could originate from worn machinery parts, upstream, or during maintenance. The sensitivity of these machines is such that they can detect metallic particles smaller than a millimeter in diameter. If a contaminated bag is identified, it is automatically ejected from the line, recorded in a digital log, and sent for root cause analysis. In high-output snack manufacturing, product changeovers are another critical concern. A single plant might produce multiple Cheetos variants: classic cheese, flamin' hot, jalapeno cheddar, and limited editions on the same line, sometimes switching several times per day. To avoid cross-contamination of flavor profiles and allergens, the factory must execute a full product changeover, which includes both physical and procedural steps. The final bags of one variant are run through the line until the seasoning and product types are completely cleared. Following that, dry cleaning and wipe down protocols are enacted on exposed surfaces. In flavor tumbler zones and powder feeding systems, residue removal is handled by a combination of mechanical vacuums, compressed air nozzles, and in some cases, wet cleaning cycles. Pipes carrying seasoning powder are often disassembled and cleaned manually or flushed with air-driven pigs, foam or rubber projectiles that scrape the interior of the tube clean as they are propelled by compressed air. All cleaning steps are verified through ATP, adenosine triphosphate, swab tests or allergen-specific strip tests to confirm the line is ready for the next product. Equipment cleaning and sanitization extend far beyond changeovers. Each section of the production line is scheduled for deep cleaning on a regular basis, with some components cleaned daily, others weekly, and critical systems like oil fryers undergoing monthly shutdowns for intensive maintenance. Every cleaning task is documented in a digital sanitation log that includes time-stamped photos, chemical usage records, technician ID, and verification by a supervisor. This log ensures compliance with food safety regulations and internal auditing systems. Speaking of oil fryers, one of the more maintenance-intensive systems in the Cheetos plant is the oil management setup. Used frying oil is constantly cycled through multi-stage filtration systems that remove fine particulates and oxidized residues. Inline sensors monitor oil color, free fatty acid content, and total polar compounds, all indicators of oil degradation. When thresholds are approached, fresh oil is introduced, and a portion of the old oil is purged to waste recovery tanks. This spent oil is not discarded haphazardly. Instead, it is captured and sent to third-party processors who refine it for use in biodiesel production or industrial lubricants, creating a closed-loop waste management process that supports sustainability goals. Seasoning systems have their own challenges in terms of dust and waste control. Cheese powder and spice blends are notoriously airborne, so extraction hoods fitted with HEPA filters are positioned above tumblers and conveyors to capture stray particles. These systems not only keep the air clean for workers, but also prevent buildup on surfaces and reduce cross-contamination risk. Powder recovered in this way is not reused in production, but is collected and weighed for waste tracking. Many factories monitor seasoning powder yield versus usage to optimize application and reduce excess without compromising flavor intensity. Additionally, factories employ floor-level waste segregation systems, where organic waste, such as broken puffs or overcooked batches, is separated from packaging materials and cleaning byproducts. Organic snack waste is often sent to animal feed processing plants or used in anaerobic digesters to generate energy, while plastics are compacted and shipped to recycling partners. These systems not only reduce landfill usage, but also lower the facility's total environmental impact per unit of product. Every phase of the factory's operation is governed by a robust system of documentation and auditing. Real-time production data is logged into the Manufacturing Execution System, MES, which connects to the plant's Enterprise Resource Planning, ERP, platform. This system allows plant managers to track every batch of Cheetos from cornmeal input to palletized output. If a quality issue is flagged post-distribution, every input, cornmeal batch, oil lot, seasoning blend, even the operator ID can be traced within seconds. This level of transparency is essential for large brands that operate under continuous scrutiny from regulators, retailers, and consumers alike. All these systems, from the air handlers and fryers to the conveyors and flavor blenders, are monitored by a central control room staffed by trained process engineers and operators. The control room acts as the nerve center of the factory. Touchscreen interfaces display real-time data on line performance, yield percentages, waste figures, and energy usage. Alarms and alerts notify the team of any deviation in pressure, temperature, fill levels, or machine health. The staff can make remote adjustments, schedule maintenance tasks, and even initiate partial or full shutdowns directly from their stations. In many facilities, predictive analytics platforms are integrated into these systems. Using machine learning algorithms, these platforms analyze historical and current data to forecast when a component might fail, how yield might shift under ambient changes, or what impact a change in oil temperature might have on puff expansion. This allows for proactive decision-making reducing downtime and maximizing efficiency. The production of Red Bull starts long before the filling lines come to life. It begins at the sourcing and logistics stage, where each raw material used in the drink is carefully specified, contracted, and verified to meet the company's global quality standards. Although the ingredient list appears relatively simple: water, sucrose, glucose, citric acid, carbon dioxide, caffeine, taurine, B vitamins, and flavorings, the level of control and traceability involved in acquiring each component is remarkably complex. We begin with the most abundant ingredient: water. Water makes up the vast majority of the product, and its quality is absolutely critical. Unlike municipal tap water used in smaller food and beverage operations, the water used in Red Bull production must conform to pharmaceutical-grade purity standards. This means it undergoes extensive filtration, mineral balancing, and microbiological testing before it ever reaches the mixing tanks. In most Red Bull factories, water is drawn from deep, protected aquifers or dedicated water sources that are tested daily. The water is pumped into on-site treatment plants where it first passes through coarse filtration to remove particulate matter like sand or debris. It is then passed through activated carbon filters to strip away chlorine, organic compounds, or any remaining trace contaminants that could affect taste or chemical stability. The next step is typically reverse osmosis, a membrane-based filtration system that removes dissolved solids at a molecular level. This process reduces the water to an ultra-clean base, free of minerals, microbes, or off flavors. Once the water is purified, it enters holding tanks constructed from polished stainless steel. These tanks are fitted with level sensors, CIP spray heads, and temperature regulation systems to maintain stability. Water is kept in motion using gentle agitators or circulation pumps to avoid stagnation and ensure readiness for blending. Meanwhile, the sugar content of Red Bull, derived from both sucrose and glucose, requires its own specialized preparation. Red Bull uses a combination of these two carbohydrates to create its sweet but not overly cloying flavor profile. These sugars are sourced from sugar beets and corn and arrive at the plant either in dry crystalline form or as concentrated syrups, depending on regional supply chains. In facilities that receive dry sugar, the ingredient is pneumatically conveyed from delivery trucks into sealed sugar silos. These silos are climate controlled to prevent moisture absorption and equipped with weight sensors to track inventory in real time. When ready for production, the sugar is transferred to large dissolving tanks where it is combined with hot, purified water and mixed using high shear agitators to create a uniform syrup. This syrup is passed through mesh filters to remove any undissolved particles, then sent to a holding tank where it is cooled and held under sterile conditions. For glucose syrup, the process is slightly different. Delivered in bulk liquid containers or tanker trucks, the syrup is pumped through heated, insulated lines to prevent crystallization during transfer. Inline flow meters and viscosity sensors are used to ensure consistency. Once in the storage tanks, the glucose syrup is sampled and tested for pH, sugar concentration, and microbial stability before being cleared for blending. Now comes taurine, one of the most distinctive and chemically sensitive ingredients in the formula. Taurine is an amino acid-like compound that plays a role in neurological development and cellular hydration. It is synthesized in pharmaceutical-grade chemical plants through a controlled reaction involving ethylene oxide and sodium bisulfite, resulting in a high-purity crystalline powder. Red Bull does not extract taurine from animal sources. It is entirely synthetically produced for purity and consistency. Taurine is delivered to the beverage plant in sealed drums or lined bags inside rigid totes. Upon arrival, each container is inspected and sampled. The contents are tested for purity using high-performance liquid chromatography and screened for heavy metals and microbial contamination. Once cleared, the powder is either stored in a dry room or moved directly to the batching area, where it is weighed with precision down to the gram using automated ingredient scales. Caffeine, another central functional ingredient, is handled with similar precision. Synthetic caffeine, which is chemically identical to naturally occurring caffeine, is the preferred form in most facilities due to its purity and consistency. It arrives in fine white powder form, packaged in airtight containers to prevent oxidation and contamination. Like taurine, caffeine is dosed in tightly controlled quantities, too much, and the drink becomes bitter or risks regulatory violation. Too little, and the expected stimulant effect may be lost. B group vitamins, specifically niacin, pantothenic acid, vitamin B6, and vitamin B12, are delivered in stabilized powder form. These micronutrients are highly sensitive to heat, light, and oxygen, so they are packaged in light-blocking, nitrogen-flushed containers. They are stored in temperature-controlled rooms and only opened at the time of production. Dosing is managed using micro-feeding systems, capable of adding quantities in the milligram range with high accuracy. Citric acid, used to balance sweetness and enhance shelf life, is one of the more straightforward ingredients. It arrives in either crystalline or liquid form, depending on plant setup. Like the sugars, citric acid is dissolved or diluted in purified water, filtered, and then pumped into blending tanks using stainless steel sanitary piping. It is included not only for flavor, but also to regulate the final pH of the drink, which has an impact on microbial resistance and carbonation behavior. The final core ingredient, prepared before blending, is carbon dioxide. Although it's added at the end of the line during filling, CO2 must be stored on-site in large insulated tanks under high pressure. This gas is certified food grade and must meet stringent standards for purity and dryness. Impurities in the gas, such as hydrocarbons or sulfur compounds, can result in off flavors or affect carbonation stability. Inline purifiers and moisture traps ensure that the gas remains within specification as it travels to the carbonation units. At this stage, all the major ingredients have been separately received, prepared, filtered, and stored in secure holding tanks, each one monitored by a network of sensors and controlled through a centralized process control system. The factory is now ready to enter the next phase, the blending and batch formulation process, where the base liquid is built step by step from these prepared components under tightly monitored conditions. Inside the blending hall of a Red Bull manufacturing plant, massive stainless steel tanks, often tens of thousands of liters in capacity, stand ready to receive pre-prepared ingredients. Each of these tanks is built with industrial mixers at the base and along the walls, with baffles designed to eliminate dead zones and ensure even distribution of all ingredients once mixing begins. These aren't just glorified vats, they're engineered systems with flow sensors, agitation controllers, and automated dosing inlets. Blending starts with the base, purified water. A calibrated volume is pumped into the blending tank. From here, the sweetener solution is added. By this point, the sugar and glucose have been dissolved into a consistent syrup in separate vessels and passed through fine mesh filters to remove any undissolved particles. They're now gravity-fed or pumped into the main tank through metered valves, which record the exact volume added in real time. At this stage, the solution is still colorless, with a mild sweetness and a viscosity slightly thicker than water. Stirring begins slowly, just enough to encourage circulation without aerating the mixture prematurely. Once the sweet base is established, the functional ingredients are added in a very specific sequence. This isn't just for convenience, it's chemical. Caffeine, taurine, and vitamins each behave differently depending on the pH, temperature, and concentration of the liquid they're introduced into. To ensure even dissolution, caffeine is dosed in carefully, often pre-blended into a neutral, aqueous solution to avoid clumping. Taurine, being more soluble, can be introduced directly, but at a steady rate to avoid localized saturation. The temperature of the blend is strictly controlled during this entire process, typically kept between 10 degrees C and 15 degrees. Keeping the temperature low helps prevent degradation of the heat-sensitive components, especially the B vitamins, and also limits the risk of microbial growth. Inline cooling jackets on the tank walls help regulate this, while digital sensors constantly send data to the factory's main control panel. After the active ingredients are in and fully dissolved, the next step is homogenization. While Red Bull is a clear drink and doesn't have oil-based elements like some emulsified beverages, this process is still used to ensure complete molecular distribution. A high-speed rotor-stator mixer is activated to subject the liquid to intense shear forces, ensuring that no microclumps or undissolved pockets remain. Think of this as the industrial version of making sure your recipe has no lumps, but at a scale where a few unblended grams could ruin an entire batch worth millions of servings. Once homogenized, the blend is passed through a fine filter system, often absolute rated filters that remove particles down to the sub-micron level. This is the final polish of the beverage, ensuring not just clarity and texture, but also eliminating any particulate matter that could interfere with carbonation or filling equipment. Now, the finished liquid base is sent to a storage tank, often referred to as the balance tank, which feeds the carbonation system. At this stage, the liquid is still uncarbonated. Carbonation must be done with surgical accuracy, both in timing and in gas levels. Too early, and carbon dioxide can escape during filling. Too late, and the drink will feel flat. Before carbonation, the balance tank contents are degassed using a gentle vacuum system to remove any dissolved air from the blend, air that could interfere with carbonation or introduce unwanted oxygen into the final product, leading to flavor instability over time. Carbonation is introduced through a high-precision saturator. This device uses temperature, pressure, and turbulence to force carbon dioxide into the liquid. The lower the temperature, the more CO2 the liquid can absorb, so the beverage is chilled further just before entering the saturator. Inside the unit, the liquid flows in a turbulent spiral while pressurized CO2 is injected. Sensors monitor saturation levels down to fractions of a gram per liter, and the flow is fine-tuned via automated valves. Once carbonated, the beverage is immediately transferred to the filler line. No storage, no delay. At this point, any agitation or exposure to heat could cause gas to escape, so the tubing, valves, and tanks are all designed to reduce turbulence. The product is now ready to be introduced into cans. Filling lines in a Red Bull factory are among the fastest and most technologically advanced in the beverage industry. The cans themselves arrive at the plant in stacks of blank aluminum cylinders, unprinted or pre-printed depending on the factory setup. These cans are depalletized automatically and conveyed upright to the rinser station. Here, they're inverted and sprayed internally with deionized water or sterile air to remove dust or particulates. From the rinser, the cans travel on a conveyor to the filler. This machine uses a gravity or counter-pressure system to fill each can precisely while preserving carbonation. The can enters the fill station, is sealed around the top rim with a flexible gasket, and then filled from the bottom up with cold, pressurized beverage. Fill levels are controlled within a margin of plus 0.5 grams to ensure legal compliance with net content regulations and consistent customer experience. Immediately after filling, the can passes to the seamer, where a pre-formed aluminum lid, known as the end, is dropped onto the top and crimped into place. This creates an airtight seal. Seamers are some of the most mechanically intricate machines in the entire facility, operating at speeds of over 1,000 cans per minute while performing multiple precision operations in less than a second per unit. After sealing, the cans are rinsed externally to remove any spillage and pass through a drying tunnel. They then enter the inspection phase. Here, cameras and sensors verify the seal integrity, check fill levels using X-ray or gamma ray detection, and inspect for dents, deformations, or labeling defects. Any can that fails inspection is automatically ejected from the line. Cans that pass all tests are conveyed to the packaging station. Depending on the market, cans are grouped in 4-packs, 6-packs, or full case trays. Robotic arms or mechanical pushers group the cans and slide them into shrink-wrap tunnels or cardboard sleeves. Once bundled, packs are palletized, either by layer robots or high-speed stackers, wrapped with stretch film and labeled with product codes, production date, and batch information. These pallets are now staged in a temperature-controlled warehouse, ready for distribution. The real-time tracking of every single ingredient, batch, fill date, and can code allows for full traceability from ingredient origin to final shipment. In the next section, we'll follow how those pallets move through the global distribution network and how Red Bull's quality assurance, shelf stability testing, and cold chain monitoring ensure that each can performs exactly as intended from Austria to Australia. With the Red Bull cans now filled, sealed, and packed onto pallets, the production process transitions into the next highly critical phase: post-production handling, distribution management, and long-term quality assurance. Although the drink is technically finished, the factory still bears significant responsibility for maintaining its integrity through storage, shipping, and shelf life. This phase involves coordinated warehouse systems, climate control, global logistics networks, and extensive quality monitoring procedures that extend well beyond the factory floor. All of it is designed to ensure that every can of Red Bull tastes and performs identically, whether it's consumed in Bangkok, Berlin, or Boston. Once the pallets are complete, they are conveyed from the packaging area into the outbound staging zone, a dedicated part of the facility built to manage finished goods. This area is laid out with barcode scanners, RFID readers, and automated warehouse software. Each pallet is scanned as it enters, recording not only the product type and production date, but also its batch code, can format, and destination market. This digital tracking ensures complete traceability of every pack produced. The system also flags any inventory that is out of rotation or that has not been cleared by the final quality audit. Pallets are stored in high bay racking systems that can reach 5 or 6 levels high. These racks are arranged to maximize airflow and minimize temperature variation, as environmental stability is critical for energy drinks. The warehouse is kept within a strict range of temperature, typically between 18 degrees Celsius and 22 degrees Celsius, and humidity under 60% to preserve carbonation, prevent packaging degradation, and protect flavor stability. Light exposure is minimized using tinted overhead fixtures or motion sensor lighting, since prolonged light can interact with the contents of clear or thin-walled aluminum containers, subtly affecting taste or causing internal discoloration. But before any pallet leaves the facility, it must be cleared through a final release protocol. This involves sampling from each production batch, typically 1 out of every few thousand units. These samples are sent to the in-house quality control laboratory for a battery of tests. Microbial testing is conducted to ensure that the beverage remains free from bacteria or yeast. Although Red Bull is not pasteurized, its low pH and high CO2 content provide natural protection, and the factory's sterile filling conditions act as a critical control point. Nonetheless, post-fill samples are incubated in climate-controlled chambers for 72 hours and checked for any microbial activity. Simultaneously, chemical stability tests are performed to verify that the concentrations of caffeine, taurine, sugars, acids, and vitamins are within tight tolerances. Each test is logged, reviewed, and signed off by senior lab technicians. Once the data passes review, the production batch is cleared for shipping. At this point, the factory releases the inventory into the hands of the logistics team, which organizes regional and international transportation. The Red Bull supply chain is designed around speed, efficiency, and protection. Because the drink is sold in more than 170 countries, it requires a global distribution system that can manage environmental variables, transit times, and regulatory differences across continents. Each factory or co-packing facility is paired with multiple logistics hubs, either operated directly or through third-party logistics providers, each specializing in cold chain monitoring, customs clearance, or last-mile delivery. Shipping conditions are tightly controlled. While Red Bull cans are shelf-stable and do not require refrigeration, they are sensitive to excessive heat and should not be exposed to prolonged freezing. Therefore, all transportation routes are mapped to avoid extreme temperature exposure. Trucks are preconditioned before loading, ensuring that their interior holds the correct temperature before the first pallet is moved in. During loading, factory staff monitor not just product count and pallet orientation, but also airflow paths and stacking height to ensure that cans are not crushed or deformed during transit. Each truck or container is equipped with temperature loggers and shock sensors. These devices record environmental data every few minutes and store it until offload. If a truck breaks down, or if the cargo passes through an area of extreme temperature fluctuation, the logs will show it. When the shipment arrives at its distribution center or regional warehouse, receiving teams will review the data. If it falls outside the acceptable range, the load may be held, inspected, or even rejected. This provides a full audit trail from the moment the product left the factory to its arrival at the next checkpoint. For international shipments, the process becomes even more complex. Export shipments must comply with country-specific food regulations. In some cases, ingredients must be declared differently. In others, labeling requirements vary. The factory works with regulatory teams to produce market-specific versions of the product, sometimes varying the language, caffeine content, or vitamin mix to meet local laws. Each international pallet is assigned a customs manifest, a certificate of analysis from the lab, and a temperature log that confirms it stayed within the specified range throughout the journey. Once Red Bull arrives at its destination warehouse, whether it's in Tokyo, Johannesburg, or Chicago, it enters a new round of inventory rotation and quality checks. Local distribution centers store the product under similar environmental controls, and the product is rotated using FIFO systems to minimize aging. While the drink has a long shelf life, usually around 18 months, Red Bull's internal standards aim to deliver most of its inventory to retailers within just a few weeks of production to ensure maximum freshness. Some pallets will be broken down into smaller loads and sent to large supermarket chains. Others are routed to gas stations, bars, vending machine operators, or e-commerce fulfillment centers. In each case, local merchandisers and sales teams monitor product placement, stocking practices, and display temperatures. Although Red Bull does not require refrigeration, many retailers choose to chill it for immediate consumption, and Red Bull provides branded refrigeration units to support this. At the store level, Red Bull continues to run random quality checks, known as in-market assessments. These include taste tests, packaging inspections, and code date verifications. Data from these assessments is sent back to the factory quality system and reviewed quarterly. If trends are observed, like subtle flavor degradation in warmer climates or denting during local transit, factory protocols are updated and packaging specifications may be revised. This feedback loop is critical to maintaining the uniform experience that Red Bull is known for globally. Even after the product has been sold, the process doesn't stop. Red Bull maintains traceability for every batch through lot codes printed on the bottom of each can. If a customer reports an issue, the quality team can pull that code, identify the exact production line, shift, and even the technician who oversaw that batch. While issues are rare, this system allows the company to investigate and resolve problems with precision, minimizing waste and protecting brand integrity. Beyond logistics and troubleshooting, the factory also conducts long-term aging tests. Retained samples from every production batch are stored under controlled conditions for 12 to 24 months. These samples are periodically tested for flavor consistency, vitamin retention, carbonation, and packaging durability. This helps inform decisions about shelf life labeling, new packaging materials, and product reformulation. Back at the plant, everything learned during distribution feeds into continuous improvement efforts. Engineers analyze transit shock data to refine pallet structures. Chemists review long-term flavor curves to tweak the balance of acids and preservatives. Operators attend refresher training sessions on fill line calibration, cap torque standards, and seaming pressure. The plant becomes not just a factory, but an evolving ecosystem of precision, designed to produce millions of cans with microscopic tolerance and global dependability. Inside Red Bull's production and R&D infrastructure, innovation continues quietly and continuously alongside the high-speed filling lines. While the mainstream drink is tightly standardized, parallel systems exist within the factory environment for development, testing, and controlled rollout of new variants, flavors, and formats. These operations are often confined to specialized pilot plants, small-scale, highly modular manufacturing lines where experimental recipes and new packaging concepts are trialed without disrupting the core production flow. These pilot lines mimic every critical phase of full-scale production, from batching to carbonation and filling, but at reduced volumes. Engineers can simulate the thermal and mechanical stresses of the full-size process, adjusting flow rates, temperature profiles, and equipment speeds to understand how small tweaks to formula or process could affect outcomes. Whether testing a sugar-free variation, a new flavor blend, or a limited edition can size, the data collected here determines what does and does not graduate to full factory rollout. Each new formula undergoes rigorous stress testing. Finished samples are subjected to cycles of heat, cold, vibration, and light exposure to simulate real-world transport and storage conditions. Flavor retention is tracked over time through sensory analysis and gas chromatography. Carbonation levels are monitored for stability across packaging types and temperatures. Packaging engineers assess how different aluminum can wall thicknesses or end configurations perform under pressure, especially when new recipes require modified CO2 saturation. If a variant clears all physical and chemical tests, the next step is consumer trials. In select cases, Red Bull collaborates with regional markets to test launch a new flavor or packaging size in a limited territory. These micro launches help measure demand, gather feedback, and identify operational issues before scaling up. Even then, these limited variants are often produced on flexible equipment lines reserved specifically for such runs, using interchangeable molds, modular filler heads, and smaller tank systems. Even small changes, like switching from a matte to a gloss label finish, require recalibration of the vision systems on the inspection line. Barcode scanners must be trained to detect label variations, and automated reject mechanisms must be tested to avoid false positives. This ensures no disruption in quality control, even when the product range temporarily expands. Back in the lab, teams also study ingredient interactions under extreme use scenarios. Industrial sugar production begins with harvesting, and depending on the region and facility specialization, the factory will receive either sugarcane or sugar beets. These two crops require distinct processes to extract sucrose, though many of the underlying steps, washing, crushing, juice clarification, and concentration are similar in principle but differ in machinery, timing, and chemical inputs. Let's start with sugarcane. Sugarcane is a tall, fibrous grass grown in warm, tropical climates. It is harvested either manually, using machetes, or mechanically using harvesters that cut the stalks and strip the leaves in a single pass. Once cut, the cane begins degrading immediately, so it must be delivered to the processing facility quickly, typically within 24 to 48 hours, to preserve sucrose content and prevent microbial activity that would convert sugar into acids. The cane arrives at the factory by truck and is offloaded into massive intake yards. These yards are equipped with cranes or grab loaders that lift entire truckloads of cane and dump them onto conveyors that feed the primary cleaning line. Before any juice can be extracted, the cane must be washed to remove soil, leaves, and insects. This is accomplished with a combination of rotating drum washers and high-pressure spray systems that bathe the stalks in recycled processed water. The water itself is filtered and reused in a closed-loop system to reduce environmental impact. Once clean, the cane is conveyed to a chopper station. Here, high-speed rotating blades slice the cane into short sections to expose the inner fibrous material. The chopped cane then moves through a shredder, a powerful hammer mill type machine that tears the cane into finer particles. This dramatically increases the surface area of the plant material, making the sugar easier to extract in the next stage, milling. The shredded cane is now ready for juice extraction via mechanical milling. This takes place in a series of large, heavy-duty roller mills, typically arranged in a tandem line of 5 to 7 stations. Each station consists of 3 rollers, 2 lower and 1 upper, that compress the cane with immense pressure. As the cane passes through each station, more juice is squeezed out. Water is sometimes sprayed onto the crushed cane, a process called imbibition, to help wash out more sucrose during the final passes. The resulting juice, known as mixed juice, is a cloudy, pale green liquid that contains not just sucrose, but also fibers, proteins, organic acids, and soil particles. What remains of the cane after this process is a dry, fibrous residue known as bagasse. Rather than being discarded, bagasse is transported to a boiler house where it is burned as fuel to generate steam and electricity for the plant itself, often making the facility energy self-sufficient. Meanwhile, the mixed juice moves to the clarification phase. Before sucrose can be crystallized, impurities need to be removed. The first step is heating. The juice is pumped through a series of shell and tube heat exchangers to bring it up to around 105 degrees Celsius. This temperature helps precipitate some of the colloidal particles and also prepares the juice for chemical treatment. In the next stage, the juice is sent to a reaction tank where lime, typically calcium hydroxide, is added. This raises the pH of the juice and helps neutralize acids, precipitate proteins, and coagulate other impurities. The exact dosage of lime is tightly controlled using inline pH meters and flow-regulated injection systems. Flocculants may also be added at this stage to help bind the fine particles into larger clumps. After chemical treatment, the juice enters a clarifier, a large settling tank where gravity separates the solids from the liquid. The solids, known as mud, settle to the bottom and are periodically removed through rotary scrapers and pumped to a filter press where the water content is removed. The resulting cake is either composted or used as a soil amendment. The clarified juice, now a light amber color and much cleaner, is drawn off from the top of the clarifier and sent to the next phase, evaporation. Let's now consider the sugar beet process, which starts quite differently. Sugar beets are harvested using machines that dig them from the soil and remove most of the leaves and dirt. At the factory, the beets are washed in flumes, long channels of water that carry the beets through a series of mechanical washers and screens. stones and heavy debris are removed using density separation, while fine silt is filtered out with mesh drums and hydrocyclones. Once clean, the beets are sliced into thin strips called cossets. These are fed into a diffuser, a long vertical or horizontal tank where hot water is sprayed over the beet slices. The water temperature is controlled to around 70 degrees Celsius and flows countercurrent to the beet material, maximizing sugar extraction. The sugar diffuses from the plant cells into the water, forming raw beet juice. This juice is then pumped to its own clarification stage, where lime and carbon dioxide are used in a process called carbonation. Calcium carbonate forms during the reaction and binds impurities, which are then filtered out, leaving behind a clarified beet juice ready for concentration. Both the cane and beet clarification processes converge at this point. They now have a clean, thin juice rich in dissolved sucrose. The next step in both methods is evaporation, which we'll explore in full detail in the following section. But for now, we've completed the complex, high-volume, highly monitored beginning of sugar manufacturing, where plant material is transformed, filtered, and chemically prepared for crystallization. Every moment of this phase is controlled with real-time feedback systems, mechanical separation equipment, and chemical treatments that must be perfectly balanced to set the stage for pure, white sugar to eventually take form. With the clarified juice now prepared, whether from sugarcane or sugar beets, the next major operation in industrial sugar production begins: evaporation. This process is designed to concentrate the diluted juice, which at this stage contains roughly 12 to 16% sucrose by weight, into a thick syrup known as thick juice or syrup, with a sucrose content of about 60 to 70%. The transition from thin juice to syrup is achieved by removing most of the water through a carefully staged thermal process. This concentration step is not just about volume reduction, it also creates the right conditions for crystallization to occur later with control and precision. Evaporation in a sugar factory is typically carried out using a multi-effect evaporator system. These systems are composed of 5 to 6 large vertical vessels, known as effects, connected in series. Each effect operates at a slightly lower pressure than the one before it, allowing the juice to boil at progressively lower temperatures. This setup significantly improves energy efficiency. Steam generated in one effect is reused to heat the next, conserving thermal energy throughout the process. The clarified juice enters the first effect and is heated with steam to just above its boiling point, typically around 115 degrees Celsius. As the juice boils, water vapor is released and rises to the top of the vessel, while the increasingly concentrated juice remains below. The steam from this first vessel is then routed into the heating coils of the second effect, where it causes the juice in that chamber to boil at a slightly lower temperature due to its reduced pressure. This cascading effect continues through all stages, progressively concentrating the juice without requiring additional high-pressure steam inputs at each stage. Throughout this process, automated sensors track the Brix value, sugar concentration, temperature, and pressure in each vessel. Flow controllers and level sensors regulate how much juice is transferred from one effect to the next, ensuring consistent residence time and thermal exposure. Operators monitor these values from a centralized control panel equipped with real-time displays and alarms. If any chamber's temperature deviates beyond acceptable limits, the system automatically adjusts steam input or juice flow to compensate. By the time the juice exits the final effect, it has thickened into a dense, amber-colored syrup with a viscosity similar to honey. It now contains upwards of 65% sucrose and has a reduced water activity, which helps to stabilize it against microbial spoilage. At this point, it's ready to enter the crystallization phase, a controlled process designed to coax sucrose molecules out of solution and into solid form. Crystallization begins in large, jacketed vacuum pans. These are vertical, cylindrical vessels where the thick syrup is further boiled under vacuum to lower the boiling point and prevent caramelization or degradation of the sugar. Reducing pressure allows boiling at temperatures around 60 to 70 degrees Celsius, preserving product quality. Inside each pan, agitators or stirrers keep the syrup moving, while high surface area heating coils provide uniform thermal input. The process begins with the introduction of a small amount of fine sugar crystals, called seed crystals or slurry. These seeds serve as nucleation sites around which sucrose molecules begin to gather and grow. The timing and uniformity of seeding are crucial. If seeded too early, too many crystals form, resulting in fine-grained sugar. If done too late, oversized or irregular crystals can result, affecting yield and downstream processing. Once seeded, the vacuum pan is held at a steady boil, and the syrup is gradually fed into the vessel in a process known as strike feeding. As more syrup enters, the crystals continue to grow while the water content is simultaneously reduced by evaporation. Operators closely watch the strike through sight glasses or by withdrawing small samples to examine crystal size and consistency under polarized light. When the desired crystal size and saturation level are reached, the strike is dropped, transferred to a large horizontal vessel called a crystallizer. Here, the mass, now called massacute, is gently stirred and cooled over several hours to allow further crystal growth and uniformity. The goal is to achieve maximum recovery of sucrose in solid form, leaving behind a thick mother liquor known as molasses. Once cooled and matured, the massacute is ready for centrifugal separation. Industrial sugar centrifuges are large, high-speed machines with perforated baskets that spin at up to 1,200 revolutions per minute. When the massacute is loaded into the centrifuge, the force of spinning flings the liquid molasses through the perforations, while the denser sugar crystals remain behind. Water or steam is sprayed onto the sugar during spinning to remove any residual molasses and improve crystal brightness. After spinning, the raw sugar is discharged from the centrifuge as damp, tan-colored granules. If the plant's end product is raw sugar, for example, in a raw cane sugar mill, this product is conveyed to dryers and then bagged or bulk loaded for transport to a separate refinery. However, in a full refining operation or beet sugar plant, further purification steps are carried out to produce white, food-grade refined sugar. The raw sugar is sent to a melter where it is dissolved in hot water to form a clear sugar liquor. This liquor undergoes multiple filtration steps, including activated carbon treatment and phosphatation or carbonatation, depending on the process. These methods remove colorants, organic compounds, and trace minerals. In the case of carbonatation, lime and carbon dioxide are added to form calcium carbonate, which binds impurities and is filtered out. After decolorization and final filtration, the sugar liquor is sent through a second crystallization stage, nearly identical to the one used for raw sugar, but this time targeting higher purity and clarity. The white sugar crystals formed in this process are sharper, brighter, and finer than raw sugar and are typically centrifuged, washed, and dried in a fluidized bed dryer. This dryer suspends the crystals on a bed of warm air that circulates through the granules, gently removing moisture without breaking the crystals. The final product is pure, white granulated sugar with a typical purity of 99.9% sucrose. It is cooled to ambient temperature and stored in silos constructed of stainless steel or food-grade plastic, protected from moisture and pests. These silos are equipped with temperature and humidity sensors, along with vibrating floors or fluidizing systems to prevent caking or compaction during long-term storage. From here, sugar can be packed into a wide variety of formats: retail-sized paper bags, industrial bulk sacks, or even liquid sugar totes, depending on customer requirements. All packaging is done in cleanroom grade conditions, using automated lines that fill, weigh, seal, and label each unit with production codes and batch tracking information. So far, we've followed the process from raw juice to pure sugar, navigating evaporation, crystallization, centrifugation, and drying. The next segment will explore how factories handle byproducts like molasses, manage energy usage with bagasse or beet pulp, and maintain food safety, quality assurance, and environmental compliance throughout continuous 24/7 operations. Now that the core crystallization and drying stages of sugar manufacturing have produced refined, food-grade white sugar, the final phases of the industrial process turn to three key pillars: byproduct management, energy and sustainability practices, and rigorous quality control systems that ensure every grain of sugar meets the specifications for purity, safety, and consistency. Modern sugar factories are not only high-output food production plants, they are also vertically integrated resource management systems designed to handle waste, generate energy, and produce multiple co-products with commercial value. Let's begin with molasses. After the centrifugation stage, once sugar crystals have been separated from the remaining syrup, what's left behind is a dense, dark, viscous liquid, molasses. This mother liquor still contains residual sucrose along with glucose, fructose, organic acids, minerals, and other non-crystallizable solids. The amount and composition of molasses can vary based on the raw material, cane or beet, the efficiency of crystallization, and the desired yield of refined sugar. In cane sugar operations, molasses is often drawn off after the second or third crystallization strike. Rather than being discarded, it's routed to molasses storage tanks, where it is either sold as a feedstock for ethanol distilleries or used as livestock feed due to its high energy and nutrient content. In some facilities, molasses is further processed to extract minor quantities of sugar through high-efficiency ion exchange or chromatographic separation, but this is only economically viable at large scale, or where sugar recovery is subsidized. In beet sugar production, molasses has a different profile, slightly lower in fermentable sugars, but rich in betaine and other organic compounds. It is also collected in holding tanks and transported in heated tanker trucks to fermentation plants, where it can be used in the production of yeast, citric acid, or industrial ethanol. In all cases, the molasses is handled under strict hygienic conditions to prevent spoilage or microbial contamination. Another major byproduct of sugar processing is bagasse, the fibrous, woody material left over from crushing sugarcane stalks. Rather than treating it as waste, factories utilize bagasse as a biofuel. It is burned in high-pressure boilers to generate steam, which is then used to power turbines that produce electricity for the entire sugar mill. Many sugar plants operate as self-sufficient cogeneration facilities, producing not only enough power for internal use, but also exporting surplus energy to nearby grids. Bagasse combustion systems are outfitted with flue gas scrubbers, electrostatic precipitators, and ash management systems to minimize air emissions and collect residual ash. This ash, in turn, may be used in agriculture as a soil amendment due to its mineral content, or it may be mixed with other waste materials to create compressed fuel briquettes. Some advanced mills pelletize dried bagasse for sale to industrial burners or biomass energy producers. Beet processing also generates fibrous residues, known as pulp. After the sugar has been extracted in diffusers, the beet pulp is pressed to remove excess moisture and then sent to drying systems, usually rotary drum dryers or flash dryers. The resulting dried beet pulp is then either pelleted or ground into flakes and sold as animal feed, particularly for cattle. High in fiber and moderately sweet, beet pulp is valued in the livestock industry for both energy and palatability. In both beet and cane facilities, the wastewater generated during washing evaporation, and cleaning operations must be treated before discharge. Factories operate full-scale wastewater treatment plants that include sedimentation tanks, anaerobic and aerobic digesters, pH correction units, and sometimes membrane filtration. These systems are monitored continuously using turbidity sensors, chemical oxygen demand (COD) analyzers, and automated flow controllers. In some operations, treated effluent is reused internally for irrigation, ash quenching, or process water, further reducing the factory's environmental footprint. Solid waste is minimized through integrated process design. Soil and rocks from beet or cane washing are separated and sent to land reclamation or construction material applications. Boiler ash, as mentioned earlier, is either reused or compacted and safely landfilled. Filter cake from juice clarification, rich in organic matter and lime, is collected and sold as fertilizer, particularly in regions where soil pH management is important for crop health. Alongside waste handling and energy management, quality control is one of the most sophisticated systems operating inside a sugar plant. From raw material to final product, multiple checkpoints are established to measure, record, and verify key parameters. Quality assurance starts with raw material sampling. Upon arrival, cane or beets are tested for sucrose content, fiber, moisture, and purity. These values inform process adjustments and predict yield per ton of raw input. In the evaporation stage, bricks, soluble solids content, is measured at every effect using inline refractometers. These instruments use light refraction to instantly calculate sugar concentration in real time. Operators can adjust feed rates, heating input, or flow pressure based on these readings to maintain target consistency. During crystallization, samples are withdrawn at set intervals and examined under microscopes for crystal shape, size distribution, and purity. Technicians monitor the color using ICUMSA, International Commission for Uniform Methods of Sugar Analysis, standards, with high purity white sugar scoring under 45 ICUMSA units. If color values trend too high, indicating the presence of residual molasses, operators can make real-time adjustments to seeding rates or massacute concentration. After drying and cooling, sugar samples are run through particle size analyzers and moisture content meters. The particle size must fall within strict specifications depending on the final use. Granulated table sugar, for instance, has tighter specs than coarse industrial sugar, destined for beverages or confections. Moisture content is typically targeted below 0.05% to ensure long shelf life and prevent clumping. Final color, purity, and turbidity tests are logged digitally and associated with specific batch codes for traceability. Packaged sugar is subjected to additional inspection. Bags, sacks, or containers are weighed using high-speed check weighers that verify fill accuracy to within plus or minus 0.2% of the labeled net weight. Vision systems inspect print clarity, barcode legibility, and seam integrity. Packages that fail any of these checks are diverted and manually reviewed. Silos storing finished sugar are equipped with real-time inventory monitoring systems using load cells and level sensors. Temperature and humidity are also monitored to prevent caking or condensation. In some regions, silos are also flushed with dry, filtered air to reduce microbial risk in high humidity climates. Across the plant, digital SCADA systems pull data from all production stages. Operators view real-time dashboards showing flow rates, temperature curves, impurity removal efficiency, and steam usage. These systems not only ensure daily operational control, but also provide long-term analytics for performance improvement. Advanced factories even deploy machine learning tools that analyze historical data to predict maintenance needs or recommend minor adjustments to maximize recovery rate and minimize energy consumption. To comply with food safety and export standards, many sugar factories operate under ISO 22000, FSSC 22000, or BRCGS certifications. This requires documented hazard analyses, allergen control programs, cleaning protocols, and traceability audits. Every production lot is labeled with a batch ID that connects back to a full production record, raw input, processing conditions, lab results, and packaging date. Customer-specific requirements are also programmed into the system. For example, pharmaceutical-grade sugar used in oral medications must meet even higher purity and microbial specifications, and may be filtered again through fine mesh screens and sterilized using UV or ozone treatments before final packaging. In some cases, sugar is converted into liquid form, known as liquid sucrose or invert sugar, by dissolving granulated sugar in heated, purified water and, in the case of invert, breaking down sucrose into glucose and fructose using acid or enzymatic hydrolysis. These liquid sugars are pumped into sterile tankers or IBCs, intermediate bulk containers, and shipped under temperature-controlled conditions to manufacturers in the beverage, dairy, or baked goods industries. Even at this late stage, the role of the sugar factory is far from static. Engineers continue monitoring consumption trends, regulatory shifts on added sugars, and regional demand to adjust capacity and format offerings. New packaging materials, biodegradable options, and energy recovery systems are constantly being evaluated and trialed, keeping the entire facility in a state of adaptive optimization. With refined sugar now stored in silos, bulk bins, or sterile containers, depending on its intended form, the focus turns to distribution, packaging, and how this versatile ingredient is tailored to the requirements of a wide array of customers, from retail consumers to massive industrial clients. This final stage is no less complex than the upstream processing phases. In fact, it involves its own dedicated systems for handling, labeling, traceability, and product customization. At this point in the factory, packaging lines diverge into three main pathways: consumer packaging, industrial bulk packaging, and liquid sugar dispatch. Each line is specifically engineered for its product format, and all are equipped with high-speed automation and real-time quality assurance systems. For retail products, such as granulated white sugar sold in 1 kilogram or 2-pound paper bags, the packaging line begins by feeding dry sugar through a vibratory chute into a vertical form-fill seal machine. The sugar passes through a flow meter and enters a funnel that drops it into a pre-formed bag made from food-grade paper or composite film. These bags are formed, filled, and sealed in one continuous motion. The machine prints batch numbers, expiration dates, and sometimes QR codes or traceability data on each bag. Each filled package passes through a metal detector and X-ray scanner to ensure that no foreign objects are present. Then, check weighers confirm that the net content is accurate within a narrow margin. Any under or overweight packages are automatically rejected and flagged for operator review. The approved bags are collected into bundles, often shrink-wrapped into 10 packs, and sent to palletizers that stack them for warehouse distribution. For industrial customers, packaging formats differ significantly. Sugar may be packed into 25 kilogram woven polypropylene bags, 50 kilogram sacks, or even 1-ton bulk bags called FIBCs, flexible intermediate bulk containers. These bags are filled using gravity-fed hoppers mounted on load cells that ensure weight accuracy. It all starts long before the fries hit the fryer. Behind the golden arches and the crunch of each familiar bite lies a factory system of immense complexity, one that spans agriculture, chemistry, precision slicing, and global logistics. McDonald's French fries may seem like simple potato sticks fried in oil, But the reality is that each one is the end product of a deeply controlled, highly optimized manufacturing process. And what most people don't realize is how much of that process is hidden in plain sight at the factory level, where McDonald's and its contracted processors manage every microscopic detail to make sure every fry, from Tokyo to Texas, tastes exactly the same. The process begins with the potatoes themselves, but not just any potato will do. McDonald's fries are made almost exclusively from specific varieties, most commonly the Russet Burbank, the Shepherdie, the Ranger Russet, and the Umatilla Russet. These varieties are chosen for their long shape, high starch content, and relatively low sugar levels, which are crucial for creating that ideal, crispy exterior and soft interior that define McDonald's fries. What McDonald's doesn't advertise is how deeply it's involved in the agricultural side of this operation. The company works directly with contract farmers, some of whom grow nothing but McDonald's potatoes on thousands of acres of land. These farmers follow strict growing guidelines dictated by McDonald's and its primary potato processors like J.R. Simplot and Lamb Weston. Everything from the irrigation schedule to the exact time of harvest is data-driven and monitored by field agronomists. Why so much control? Because if the potato's sugar level is too high, the fry will burn in the oil, turning dark brown instead of golden yellow. If the potato has too much moisture, it will steam instead of crisping. And what's often hidden from view is the extensive sorting and testing done before the potatoes even make it to the processing plant. Once harvested, potatoes are stored in high-tech facilities that carefully regulate humidity, airflow, and temperature, often between 45 degrees Fahrenheit and 50 degrees Fahrenheit, to prevent sprouting and sugar buildup. At this stage, the potatoes go through a phase known in the industry as curing, which helps them develop a tougher skin and reach the desired sugar-to-starch balance. McDonald's factories don't reveal much about this curing phase, but it's one of the most critical elements to ensure that the potatoes will fry up properly when they finally reach your tray. When potatoes arrive at a McDonald's processing facility, many of which are run by their longtime partner, Simplot, they're subjected to a barrage of sorting and quality control tests. The first step is visual sorting, where cameras and AI-powered systems scan each tuber for defects, bruises, blemishes, and anything that would impact final appearance. Those that don't meet the exact standards are removed. But what most people don't know is that the internal sugar content of the potato is also tested using sophisticated near-infrared scanners. Potatoes with sugar levels, even slightly outside of spec, are rerouted to other uses or discarded entirely. After sorting, the potatoes are cleaned in an intense, multi-stage washing process. They pass through flumes, essentially water slides, where dirt and debris are blasted away by high-pressure jets. Then, they're scrubbed mechanically in abrasive drums and visually re-inspected. By the time a potato reaches the peeling phase, it's already undergone more inspections than most food products receive in their entire life cycle. Why? Because McDonald's doesn't just want quality, they want standardization. Each fry must look and taste the same, regardless of whether it's cooked in Malaysia or Montana. Peeling is done using a high-pressure steam system. The potatoes are loaded into a sealed vessel and blasted with superheated steam for just a few seconds. This causes the skin to loosen rapidly. As soon as the pressure is released, the skins separate and are rinsed away. What remains is a completely peeled, pristine potato ready for slicing. But the slicing is not random. It's done by a process far more mechanical and mathematical than most people would guess. The peeled potatoes are shot at extremely high speeds, up to 60 miles per hour, through a grid of stainless steel cutting blades known as a water knife. These blades slice the potatoes into precise lengths and widths, typically around 0.28 inches thick and up to 3.5 inches long. The water jet ensures minimal friction and deformation, which is especially important for keeping the fries straight and uniform. In the background, software algorithms are constantly adjusting cutter feed rates and blade sharpness to match the physical properties of each batch of potatoes. But here's where the first secret really kicks in. Once the fries are cut, they don't go directly into oil. First, they're blanched in hot water, typically between 160 degrees Fahrenheit and 170 degrees Fahrenheit, for several minutes. This is a crucial but rarely discussed step. The blanching process serves multiple purposes. It removes excess sugars to reduce browning during frying. It gelatinizes some of the starches to create a smoother exterior. And it partially cooks the interior to ensure the fry finishes with the right soft texture after final frying in store. What's less known is that this water may be treated with additives, like citric acid or sodium acid pyrophosphate, to preserve the color of the fries and prevent graying during storage. After blanching, the fries are rapidly dried in a high-powered air system. This air drying tunnel removes surface moisture to prepare the fries for the next step, the first fry. Yes, that's right. McDonald's fries are fried twice, but the first time doesn't happen in your local restaurant. It happens at the factory. The pre-frying phase is done in massive vats of vegetable oil heated to around 375 degrees Fahrenheit. The fries are cooked for just 45-60 seconds, long enough to create a light outer shell, but not to fully cook the interior. This brief fry locks in the shape and starts forming that distinct McDonald's fry texture. After this flash fry, the fries go straight into a blast freezer. In a matter of seconds, their temperature is dropped from over 300 degrees Fahrenheit to well below 0 degrees Fahrenheit. This locks in moisture, halts cooking, and extends shelf life for months. The result is what's known in the industry as a par-fried product, partially cooked, frozen, and ready to finish. Once the freshly par-fried McDonald's fries exit the industrial fryers, still golden but only partially cooked, they enter one of the most carefully engineered steps of the entire production process: freezing. This phase is far from ordinary. The secret to locking in that signature McDonald's fry texture and color involves cryogenic speed, airflow science, and microcrystal management. Every fry is treated not as a raw potato product anymore, but as a finished structure in progress, one that must be preserved in a state of suspended readiness until it is reanimated in the deep fryers of restaurants across the globe. The fries are conveyed directly from the oil fryers to a blast freezing tunnel. This isn't your average cold room. It's a highly pressurized, continuous flow freezer capable of dropping product temperature from over 350 degrees Fahrenheit to well below 0 degrees Fahrenheit in less than 5 minutes. This rapid freezing is key to quality preservation. Why? Because fast freezing forms tiny ice crystals within the fry's cellular structure. These microcrystals are less damaging than larger, slower formed crystals that rupture cell walls and lead to mushy textures when cooked. McDonald's suppliers invest heavily in ultra-fast freezing systems to ensure that every fry maintains its structural integrity from factory to fryer. Inside the freezer, conveyor belts carry fries through multiple zones where the temperature is dropped in controlled increments. Powerful fans circulate ultra-cold air in a laminar flow pattern, creating a uniform freezing effect across each fry's surface. Sensors inside the chamber measure air velocity, temperature, product thickness, and moisture levels to adjust fan speeds and refrigerant input in real time. The goal is a fully frozen product with a moisture content that stays just right. Not too dry, not too icy, so that the final fry will puff and crisp just the way McDonald's demands. But before these frozen fries are boxed and shipped, one more step takes place. One that most consumers never think about: anti-clumping treatment. Because McDonald's fries are thin and uniform, they're at risk of sticking together once frozen, especially in high moisture environments. To counter this, a microscopic layer of dextrose is sometimes applied after blanching and before freezing. This coating is not added for sweetness. It's there to assist with color development and minimize the chance of oxidation during storage. It also subtly enhances surface crispness during the final fry. In some factories, an even more specialized process is used. A combination of sodium acid pyrophosphate and citric acid may be sprayed on the fries, pre-freezing to lock in that golden hue. This solution prevents enzymatic browning and further stabilizes the fry's color even after months in frozen storage. It's a step that might seem unnecessary, but in the McDonald's system, where fries are shipped internationally and cooked under variable conditions, it's part of the formula for total consistency. Once fully frozen and treated, the fries are transported to the packaging line. This stage is fast, automated, and highly controlled. Fries are weighed using combination scales, which use dozens of small buckets to calculate the perfect load. Whether it's 2.5 pounds bulk bags for food service or 10 pounds cartons destined for regional McDonald's distribution centers. Each batch is fed into high-speed form-fill-seal machines where plastic liners are formed from reels of film filled with frozen fries and sealed airtight. Oxygen is flushed from the bag and replaced with inert gases like nitrogen to extend shelf life and prevent freezer burn. Each bag is labeled with batch codes, facility information, and freeze dates. These bags are then placed into corrugated cartons, which are automatically stacked onto pallets and shrink wrapped. The pallets are scanned into the facility's warehouse management system and stored in vast, temperature-controlled storage rooms maintained at below -10 degrees Fahrenheit. From here, they wait, sometimes just days, other times weeks, before being dispatched to a McDonald's distribution hub. What's rarely discussed publicly is just how advanced the inventory system is. Every pallet of fries is tracked from the moment it's boxed to the moment it's unloaded in a restaurant kitchen. If there is ever a concern about quality, contamination, or shipping damage, McDonald's corporate and their suppliers can trace every fry down to the production line, fryer, and time of day it was processed. This traceability isn't optional. It's embedded in food safety protocols, legal compliance systems, and global quality assurance audits. When the fries finally arrive at a McDonald's restaurant, they're still not done. They are stored in walk-in freezers until ready for use, where conditions must be monitored and logged to ensure the frozen state is never compromised. A fry that partially thaws and refreezes will develop ice crystals, lose crispness, and underperform in the fryer. Every crew member in the kitchen is trained to handle the frozen product delicately, shaking bags to loosen clumps, never overloading the baskets, and minimizing the time between freezer and fryer. And now, the final fry begins. In store, the frozen fries are dropped into preheated oil, specifically a blend of canola oil, corn oil, and soybean oil. However, what most consumers don't know is that this oil is carefully filtered and changed according to a strict schedule. Filtration systems inside each fryer remove particles of carbonized food and prevent oil breakdown, extending usability while maintaining the clean, light flavor McDonald's demands. The oil is tested multiple times daily for free fatty acid levels, color, and foaming to make sure it hasn't deteriorated. If any reading goes outside McDonald's specifications, the oil is discarded and replaced. The frying process in store lasts precisely around 3 minutes at roughly 168-175 degrees Celsius, depending on local settings and fryer model. During this time, the moisture inside the fry flashes to steam, puffing the interior slightly while the exterior rapidly crisps. Those tiny air pockets created by the factory blanching and flash frying now finish the transformation. And the secret to McDonald's uniform texture? It's those pre-engineered starches and exact cook times. When done properly, the fry is lightly golden, stiff enough to hold its shape, and just soft enough inside to match the one you had years ago. Seasoning is also precisely measured. As the fries are shaken from the fryer basket, they're dropped into a stainless steel holding tray and dusted with a uniform dose of pure, fine-grained salt. The salt granules used by McDonald's are specially selected for size and shape, large enough to adhere to the surface oil, but fine enough to dissolve quickly on the tongue. Shakers are calibrated, and portion control guidelines ensure consistency across locations. And here's the last hidden layer of control: the fry holding time. McDonald's dictates that fries must be served within a very specific window after cooking, usually no more than 7 minutes. After that, they're discarded, even if they appear fresh. This strict timer is part of the reason your McDonald's fries are often hot, crisp, and consistent. It's also one of the reasons you'll rarely see a fry sitting under the heat lamp for long. While most McDonald's fans recognize the signature taste of their fries almost instantly, few understand just how orchestrated that flavor really is, or how it's achieved through a global network of tightly controlled suppliers, additive strategies, and ingredient choices designed to replicate a flavor memory baked into the global food consciousness. The story of McDonald's French fries isn't just about potatoes, oil, and salt. It's about manufacturing identity, reproducing the exact same sensory experience for billions of customers each year, regardless of where or when they eat them. To understand how McDonald's does this, you need to look beyond just the factory floor. Behind the scenes is a system of global standardization that governs everything from agricultural inputs to packaging films. Simplot, McCain, and Lamb Weston are the primary suppliers of McDonald's fries, and each operates massive, dedicated processing plants, some of which process hundreds of thousands of pounds of potatoes per day, exclusively for McDonald's. These facilities are synchronized with a global specification book that dictates the required fry length, thickness, shape, sugar tolerance, moisture range, oil absorption, and post-fry texture. And then there's the flavor. Many consumers don't realize that McDonald's French fries are subtly flavored before they ever reach the restaurant. For decades, McDonald's fries were cooked in beef tallow, a rendered fat from cattle, that gave them their distinctive, rich flavor. But by the 1990s, amid rising health concerns and cholesterol awareness, McDonald's phased out animal fats and replaced them with vegetable oils. This change had a major impact on taste, prompting backlash from loyal customers who noticed the difference almost immediately. What most people don't know is how McDonald's responded to that backlash, not by returning to beef tallow, but by recreating its flavor synthetically. Today, the par-fried fries that leave the factory are flavored with a natural beef flavor additive. This additive is applied during the pre-frying stage or infused into the frying oil and contains hydrolyzed wheat and milk derivatives. It's designed to replicate the rich, meaty aroma once delivered by tallow, but without using actual beef fat. This additive is one of the most closely guarded secrets of the entire process. It's what gives McDonald's fries that faint umami backbone that makes them taste savory in a way that purely plant-fried potatoes often do not. And while this additive is labeled as natural flavor on ingredient lists, its composition is highly engineered by flavor chemists and tested repeatedly to ensure it holds up under freezing, frying, and heating conditions in restaurants. The flavor system doesn't stop at aroma. Texture plays a role too. McDonald's fries are engineered to crisp on the outside and remain soft in the middle, and achieving this consistently across markets is an engineering challenge. The crinkle-like effect of the outer skin is partly due to starch modification. Some potato slices are lightly coated with a thin layer of modified starch before freezing, an invisible layer that reacts in the fryer to create a delicate crust, locking in moisture and helping the fry maintain a longer crisp life under heat lamps. This crust is not easily visible, but it is critical. Without it, fries would quickly become limp and oily within minutes of cooking. With it, they hold their shape, resist sogginess, and retain that gentle crunch even as they cool. And although McDonald's does not add batter to its fries, as some fast food chains do, This ultra-thin layer of modified potato starch acts in a similar way, without compromising the all-natural image. Regionally, the manufacturing process must adjust for climate, regulation, and local preference without changing the end result. For example, in India, McDonald's fries do not contain the beef-derived flavoring found in the US to respect dietary and religious restrictions. In Muslim-majority countries, fries may be certified halal and produced in dedicated facilities to ensure separation from non-compliant products. These adjustments require dedicated supply chains, custom formulation runs, and regular taste panels to ensure that the final fries remain indistinguishable from their global counterparts in look, feel, and taste. Flavor consistency is upheld using trained sensory teams who sample fries from different global markets and compare them to reference standards kept in controlled storage. These panels evaluate crispness, oil profile, salt adhesion, internal moisture, mouthfeel, and aroma. If a discrepancy is detected, for example, fries from a factory in Southeast Asia are crispier than those in the US, engineers can investigate and recalibrate oil composition, blanching temperature, or drying time to rebalance the product. And there's more. Packaging. Even the packaging for McDonald's fries is a product of manufacturing science. The familiar red carton is designed not just for branding, but for thermal control and grease resistance. The paperboard is treated with a food-safe coating that prevents oil soak through, and the shape of the carton, with its slightly flared mouth and deep vertical pocket, is calibrated to maintain heat without trapping steam. Fries are less likely to sweat inside these containers compared to traditional closed boxes, which helps preserve texture even during transport or delivery. In the supply chain, those frozen fries move through an equally engineered logistics network. From factory freezers, they're shipped in refrigerated trucks, often under continuous GPS and temperature tracking. Distribution centers store them in walk-in freezers maintained below -10 degrees Fahrenheit, and restaurant deliveries are timed and logged to minimize thaw risk. McDonald's tracks fry inventory down to the store level, forecasting usage based on PCPOS data, and adjusting regional deliveries in real time. If a freezer malfunctions, the system flags the at-risk batch immediately, allowing a preemptive product pull before a customer ever notices. Back in the restaurant, staff are trained using digital timers, fry chart cards, and standardized scoops to portion, salt, and serve the fries. McDonald's restaurants even perform fry station audits to check adherence to hold times, oil filtering frequency, and batch rotation. These audits happen regularly, often without notice, and are tied to store performance metrics. Managers are held accountable for fry quality just as they are for speed of service or cleanliness. Despite all this control, McDonald's fries do have one unavoidable weakness: time. Even with starch systems, flavor additives, and optimized packaging, fries lose their peak texture within minutes. That's why McDonald's limits the hold time in the warmer to around 7 minutes. After that, fries are discarded, still edible, but no longer acceptable by brand standards. This results in significant waste, but it also maintains McDonald's reputation for fresh tasting fries, even if they were frozen and processed weeks earlier. So what are McDonald's factories really hiding? Not deception, not shortcuts, but the scale and precision of industrial food science operating behind something as simple as a fry. The way a potato is selected, how it's processed, flavored, partially cooked, frozen, stored, shipped, fried again, and even salted. All of it is engineered to deliver that one familiar experience. Hot, golden fries that snap slightly when bitten, give way to a tender interior, and leave a subtle beefy aroma in their wake. What they're hiding is just how much work it takes to make something look so effortless. The real secret of McDonald's fries is that there are no accidents. Every element, from starch composition to carton geometry, is designed. And in a world where people crave predictability in their favorite foods, That's exactly the point. The next chapter in McDonald's French fry production isn't just about improving what already exists. It's about redefining how the entire process can evolve under new technological, environmental, and consumer health expectations. While the current system has been fine-tuned over decades to deliver uniformity and mass appeal, the future introduces challenges that can't be solved by simply optimizing old methods. Automation, artificial intelligence, sustainability, and evolving nutritional preferences are all converging to push McDonald's and its processing partners into the next phase of fry manufacturing. One of the most notable developments is the rise of advanced automation and AI-driven process control. In modern McDonald's fry facilities, machine learning algorithms are already being piloted to monitor real-time data from every stage of production. Sensors embedded along the slicing lines, blanches, fryers, and freezers send continuous streams of information: potato dimensions, sugar content, moisture loss, oil flow, fry color, and more. These AI systems analyze the incoming potato crop and dynamically adjust settings like blade calibration, blanching time, or oil temperature to match variations in raw material quality. Instead of relying on preset recipes, the system now learns and adapts, helping reduce inconsistencies and food waste. In parallel, robotics are making inroads not just in manufacturing, but inside McDonald's restaurants themselves. Frying stations in pilot stores are being equipped with robotic arms or automated baskets that load, cook, and shake fries with no human input. This standardizes cook time and reduces operator error, ensuring that each batch is fried exactly to spec, regardless of shift or staff turnover. For McDonald's, this reduces labor costs, improves food safety, and eliminates variability in fry texture and temperature. Sustainability is also driving significant changes. One of the key pressures on the current model is oil usage. While McDonald's already employs rigorous oil recycling and filtration protocols, new systems are being trialed that extract even more particulates and extend oil life significantly without affecting flavor. Some suppliers are exploring high-efficiency fryers that use vacuum environments to lower frying temperatures, reducing oil absorption and energy usage. McDonald's is also quietly funding research into lower oil par-frying methods that could replicate crispiness using air-based thermal systems, potentially paving the way for a future where fries are air-fried in-store rather than deep-fried. Water usage is another sustainability frontier. The massive amounts of water used in washing, blanching, and rinsing potatoes are being addressed through closed-loop recycling systems and precision spray technologies. Instead of full immersion, some newer systems use high-pressure misting to clean and treat potato surfaces, cutting water usage by up to 40% per ton of potatoes processed. Every gallon saved matters when facilities are producing millions of pounds per week. Health consciousness among consumers is also influencing the future of McDonald's fries. Although the company has already shifted to trans fat-free oils, the next step may involve reducing sodium or introducing new seasoning options. Internally, there's ongoing experimentation with lower sodium salts that maintain the same flavor perception with less actual sodium chloride. Other ideas under consideration include sweet potato or blended vegetable fries, though any change to the core offering would require monumental testing to avoid alienating loyal customers.